Hello there, hello everybody, and welcome to this final project presentations ceremony. We have a very exciting day ahead, and we are going to have today 5 final project presentations by our masterclass students. We are going to start now with the presentation by Naveen, which is titled Starbo AI Cafeteria. We will continue after this one with the presentation by Jēkabs, which is titled Autonomous Trash Table Picker Robot.
Okay, excellent.
Next, we have a presentation by Robert Gruberski, which is titled How to Build a Real Roast Robot from Scratch, a Journey Diary.
Excellent.
Very interesting.
Yes.
We are going to have next the trash table detection using only Lidar sensing project by Ritwik Rohan. And to close the day, we are going to have the presentation by Peera, Tienthong, which is titled Autonomous Shelf Detection with a Mobile Robot Using Behavior Trees.
So we have, let's say, like 4 types of projects to be in this session of today. One is about the table detection and carrying to one place. This is one. Second one is going to be about an arm grasping a cup of coffee. Then we have a project of a full robot built using ROS techniques. And then the final one is the warehouse robot that carries the shelves and puts it at the proper place. So
exactly.
That's the summary.
Yeah.
Then can we start with the first one?
Yeah, so let's get started with the first presentation by Naveen. So let's say hello to Naveen. Hello there.
Hi everybody, how are you all? Hi Mr. Ricardo, hi Alberto, how are you?
Fine, very good. Excellent. So excited to hear about what you have achieved as the final project of the masterclass. Are you ready?
Yeah, I'm ready.
Wait a second. Can you confirm that
everything is fine?
Everything is fine. Yukon? Can you confirm? Yes? Okay, you can hear. Okay, then go ahead, Naveen.
Yeah, the audience is yours.
Okay, let me share my screen. Is my screen visible?
Yes.
Yes.
Okay. So before starting with the presentation, I would like to say everyone that, did you all know that almost 44.7 billion cups of coffee is being consumed by humans per day?
No,
when I saw this number, I was like astonished,
Yes.
So huge. And, but personally, when I was having a full-time job, I used to visit the cafeteria 3 to 4 times a day and spend a lot of time there, about 30 minutes chatting with my friends. And my manager used to get really pissed about that. So I was like thinking about enhancing the experience of cafeteria. And I was just thinking, how about the cafeteria comes to you instead of you going to the cafeteria? So that was, I didn't just stop thinking, but I wanted to put this into action. And this is how I came about with the Starbots.ai cafeteria. So this is the automated cafeteria setup with the coffee machine, cup dispenser, and the barista mobile robot. And this is going to make coffee for us today. So yeah, this was an older setup of the Starbots AI. So I'm going to talk about the bigger picture here. So the cafeteria, the bigger picture of the cafeteria was, the arm, the robotic arm is going to pick up the coffee cup from the dispenser and it's going to put it on the coffee machine, and the coffee comes out and it keeps on the table, and the robotic arm picks up the coffee and then puts it back on the barista mobile robot, and the robot goes and delivers it to the table. But our scope of the project is just picking up the coffee cup and placing it on the barista. That's what we're going to see today. Okay, so this is a demo which I've recorded earlier, and I wanted to share this with you at the starting of the presentation. Okay, so now before I go on to explaining the goals and problems and the platforms which I've used, I wanted to make sure that everyone understands the flow of my program. So I have 2 entry points to my program, which is Google Assistant and website. So these are 2 triggers. So I use IFTTT webhook and REST API triggers, which goes to Jenkins, and Jenkins is directly launches the ROS2 launch files. So, we have the robotic arm which coordinates with Barista, and we have a perception system which is AI based. And this picks up the cup and places on the Barista. This is how we can put it very simple, in simple words. Okay, so we'll see more about this in detail. So I wanted to start off by giving the pillars of my Starbo AI. So let's start with the UR3E arm. So this is the protagonist of my project. So basically, this is the arm which coordinates with all the other devices, the coffee machine, dispenser, the cup, and the barista robot. So to operate this arm, I'm using OMPL default planner and KDL inverse kinematics for this. So basically, this is the arm. This is the hero of my project, and it's the main picture. And yeah, next, let's go on to the perception. So now things are getting a little bit challenging because I know the cup is there on the table, but I don't know where it is, right? So the cup is exactly right in front of my eyes, but the robotic arm will not know where it is. And at the construct, we always prefer innovation. So I was like, okay, instead of using point clouds and just advanced image processing, I was like, why don't we just go and do some AI stuff here, do convolutional neural networks. So I thought, okay, I started training on my images, and then I got a good output, which you'll be seeing in the further slides. So using perception, I am detecting the object and localizing the position of the object. And based on that, the robotic arm will go to that position and pick up the cup. That's that simple. And Barista. So this is the Barista mobile robot, and it doesn't have a lot of scope in my project here, but as a full picture, it is the delivery manager. It's going to deliver the coffee cups to the tables or to the people who ordered it. Okay, so in my scope of the project, the robotic arm picks the cup and places right into the cup holder, which is a little bit challenging because the diameter is exactly a little bit, it's just very, bigger than the cup. That's it. So that's a little bit challenging because if I move a little bit, if the arm moves a little bit, it's not going to drop it in. The next one is my website. So this is my website, which we're going to use it in a few minutes. So I'm going to show it very quickly what my website is about. So this is my, can you see my screen, the website? Okay.
Yes, we can.
Yes. So this is the official starbots.ai website. And here, this is the place we'll be placing the order. We just type in our name, email, and order a coffee. You'll be able to order the coffee. Just pick up the cup and place it on the barista robot. So we have a menu here. This is for the bigger picture. And, this is me. These are testimonies. And our robotics team, the UR3 arm, it's a maker. And I'm the head of starbots.ai, by the way. And yeah, this is the website. You'll be seeing it in a few minutes. Okay, so let's go back to the presentation.
Naveen.
Yes.
Are you hiring currently or?
Yeah, I'll nominate you as Chief Technical Officer.
Okay.
Please join my team. Okay, now let's go to some serious part, the goals of my project. Okay, so first of all, planning trajectories. I was telling, just start from position A, start from cup dispenser to go to the coffee machine, pick up the cup, going to the barista. How will the robot know from where to start and where to end, how to go? The robot is not going to know. And when you saw this, at a closer look, the cafeteria is tightly packed. It has a wall, huge wall there, and a table and coffee machine. And when it moves, it's gonna hit something and crash, and it's gonna stop. I did it. Without planning. When I did it, I hit the wall multiple times, and I had to wait a long time, to get it rectified. So this happens. So this should not happen in the production side of the robot, right? So what is actually necessary here is the planning. A planning scene is required. That is how I achieved this. So I created a wall and a barista robot. This is the coffee machine and this is the cup. So it's going to pick up the cup and it goes up and it places on the barista robot. When it picks up, the color changes, right? Because the state of the robot is changed. And now it places on the barista. Because when suppose if the planning is not there, the robot can go clockwise as anti-clockwise as well. If it goes anti-clockwise, it's going to hit the wall and going to stop, right? So this, to avoid this, we are using planning scene. So next is perception. This is where I've implemented the AI concept. Okay, so, and it's very important to detect the object and localize it, because a slighter variation in the detection will make the, will not grasp the cup. The arm will not grasp the cup if there's any variation. So what did I do when I did the simulation? When I did the simulation, I used something called contours. Contours are like the curves joining, and it highlights all the uniform intensity values. So when you see the simulation, it's completely dark backside. There's no hindrance, nothing is there. So I was easily able to detect the cup. So I thought I was like, okay, the Ross engineer, I easily detected the cup in just seconds. Then I was very confident when I tried this on the real RGB image. I just had a mess on the screen. So see, can you see? I can't even see what contours it's detecting. So the contours work only on simulation, but in a real noisy world, it did not work. So I had to come up with a solution, and that was the CNN network. So what I did is I took 50 images of the cup. So basically cups like this. So I moved a lot of positions here and there with the arm, and it took me really a day to do that. But I took all the 50 images and I trained a convolutional neural network with the bounding values. This will be W, this will be X, Y, W, H. So based on this, I trained a neural network, multi-folded. Yeah, yeah, audible. Yeah. Is the screen visible?
Hello, hello.
Hello?
Yes, Naveen, can you hear us?
Yeah, I can hear you. Yeah.
Okay, I think we are good.
Okay, yeah. Okay, so yes. So it was not that simple, getting the centroid of the RGB image and posting it over the depth image is not simple, because the RGB image has different dimension and the depth image has different dimension. It's 180 cross 320 and the depth image is 240 cross 320. So what did I do? Using a gripper, I calibrated the pose offset. So I kept the centroid manually on the gripper, and then I positioned it the same gripper using manual trial and error method. I got it on the center of the gripper, and based on that, now I have the pose offset calibration X and Y values.
Ahora ha vuelto,
Right?
pero el tío no va, ¿no?
So
Yes, Naveen, you can continue.
So how did I detect the cup? So this is 42 images where you're able to see different positions of the cup. And I've detected this bounding box and the centroid. It's based on neural networks, multifolded layers. It has a convolution layer, and it's based on Adam optimizer. Okay. And the error function which I used, loss function which I used is mean squared error. Okay. So let's go to the barista. What is a problem with the barista? So barista is in my project, it's going to be fixed. But the only issue here is diameter of the cup holder is almost equal to the cup's diameter, because and if I try to incline the arm in some way, the cup is not going to fall inside the barista's cup holder. So I have to be very careful here. So that I used joint trajectory values. I set a joint state space goal, and with highest precision, so that it doesn't go here and there, and the cup doesn't fall outside the barista. So now let's quickly see the simulation which I've done. So if you see here, there's no wall, so it takes anti-clockwise direction, and it goes and grabs the cup. After that, it does a clockwise direction because there's no wall here. And now it goes to the barista, and it's a Cartesian path, and then drops the cup on the barista. Calculation is successful. Now, the next one is the real robot. I'm really excited to show you all the real robot. So I think, is the screen visible? Real robot. Okay.
Yes.
Okay. Okay, fine. Yeah. So now
That's in real time, huh?
Yeah, it is in real time. Yeah, it's Starbot, the construct.ai. Real time, and I can just load it. Yeah, okay, fine. So here, so first I'm going to run a node, which is it's called raw broadcaster, because there are some issues with the concurrent connections with the camera. I'll not be able to detect the capture the RGB image and the depth image simultaneously. So what happened is I'm gonna create subscribers, which is gonna subscribe to RGB image first, and then to the to the depth image. It just goes one by one, one to one, one to one. Okay, so I'm just gonna launch that, and now we have the website ready. Okay, website is ready. Everything is running. I think it's time that we go and launch our project. Naveen. And now let's order a coffee. Who's excited for the coffee? So yeah, here there's an image, but I'll show you this is the status screen. We'll have the image, order status. I'll show you the project screen. So, yeah. First, we got the perception output here. Perception output is here. And now it's time for the robot to launch. Yes, it's launching. So now I'm using a joint space goal to reach a home position. From there, I'm using Cartesian paths to go about X and Y directions. And from here, it's going to pick up the cup. Oh, okay. There's some issue here. Yeah. Let me quickly restart it.
So it seems like the gripper didn't close, right, Naveen?
Yes, exactly. Let me quickly restart. So this is based on Jenkins. So I'm just stopping the Jenkins, you know, program. Okay. I think this time we'll be good to go. Okay. I'm getting the image. Now let's start again. It's okay. Let's go to the screen. Okay, we have the perception. It's the same issue again.
So what's the situation now, Naveen?
It's the same issue. I'm just canceling the job and I'm running it again.
Okay, we can see now your presentation only.
Yes.
Can you share your screen? Maybe we can see what you are doing. Yes. So now you are launching.
I'm launching the node again for the images. Uh,
Maybe you can put a title on the different tabs so you know clearer.
okay, so now let's quickly check the perception.
Okay.
Okay, I think the perception has launched. Okay, then let me re-trigger the job again.
Mm-hmm. So you are launching this job through
Through my
the
website.
web page.
Yeah, web page. Yeah.
Okay. And this is the camera, the current situation right now. You can see the robot was kind of trying to put something on the other robot.
Maybe
The arm.
maybe you can try, Naveen, to send a goal directly to the Gripper to see if it responds.
Mm-hmm. Let me check this. I've triggered the job. Let's check again.
Okay.
Last time.
Yeah, sure.
Okay, the perception system works now.
So we have to remind to the audience that this is what tough guys, tough engineers do. Okay, so here Naveen is showing in real time with a real robot how everything works. And then sometimes things happen.
It's gonna start in a few seconds.
Yeah, we have confirmation from Rodrigo that the gripper is working, so it should work. Okay, so what do we have now? Naveen, the robot
we
is
have robot is going to home position.
Okay.
From there, take the Cartesian path towards the X and Y poses. Oh, okay, yeah, now it works.
yes, is closing is
Yes.
Please continue your description, please.
Yes, yes, it's closing the cup, and once it closes, it's going to lift up to using Cartesian path, and then it rotates the arm using joint state space goal. And this is my second home position. This will be my second home position. Yeah, this is my second home position. And from here, I'll use the Cartesian path to go down the z-axis towards the raw sticker. And from here, I'll be able to go to the whole zero using joint state space goal for utmost accuracy. And from here, I'm going to drop the cup. Yes, the cup is dropped successfully. This is my home position. And this is how the pick and place works. And yeah, the first two times it failed because it was an issue with the perception. You know, the perception did not launch properly, and that was an issue. I did not test it before, so that was an issue, but now it's working fine. And now I have a last one, another simulation, another demo to show, for which let me launch my phone screen. Okay. Is my phone screen visible?
It says loading, yeah?
Still working on it, it says.
So we are going to see your phone now here, Naveen?
Yes, exactly. Just a quick, suppose if the entire cafeteria setup is there in the business production, and in case if these people, the customer doesn't pay, we're gonna take the coffee back, right? I'm just gonna do that.
Yeah,
So
sure.
Excellent.
Hey Google. Hey Google. Oh, my Google doesn't work. Hey Google. Hey Google. Okay, let me launch it manually. Activate cancellation sequence.
Got it. Activating cancellation sequence.
Yeah, so I asked Google to launch that cancellation sequence. Let's see how it works. So now what's going to happen is when the customer doesn't pay for the coffee, I'm going to take the coffee back. I'm not going to ask the barista to go deliver it. Until he makes a confirmation, no delivery. So the cup stays on the barista. And now once I launch this, it's going to go down and grab the cup again. No excuse, no sacrifices on the payment. I'm going to pick up the cup and I'm going to drop it on X. So I'm using the joint space goal to reach the cup for much accuracy. And then I'm using Cartesian path to go up on the Z axis Then this is my home position, and then I do a rotation using joint state space goal towards the X mark. And from there, I'm going to go down on Z axis using Cartesian path. I'm just going to open the gripper. Yeah. Yes. Okay. So we've ensured our business is going live, like we'll survive. So
very good point.
So last, let me talk about the future enhancement. So yes, so basically the future enhancements. I wanted to work on a fully functional setup using a cup dispenser, coffee dispenser, everything, and try different inverse kinematics plugins and planners on the setup and analyze which is going to be the best one to make this fully functional and automated. And I wanted to build an AI cafeteria, which dispenses coffee based on the mood of the customer with an app or something. It detects the mood and it gives matcha latte or cappuccino, Americano, anything based on the mood, sentiment analysis and all. So the next one is the scope of perception. If you see, I've just trained my model just around the X mark, a little bit, a few centimeters away from the X mark, not the entire table. So as a future enhancement, I wanted to train it on the entire table. So wherever the cup is, it's going to be able to detect using the RGB camera, and it's going to pick up and place it on the barista robot. That's my future enhancement. And thank you so much. And special thanks to Girish, Rodrigo, Alberto, and my mentor, Mr. Ricardo. Without these people, I wouldn't have been able to do the course and as well as the masterclass project. Thank you so much, guys.
Excellent work, Naveen.
Thank you. I can see you.
Yeah, the crowd is super excited here.
Yes.
Is it?
Excellent.
Thank you, guys. Thank you so much.
Wow, it's been impressive. Yeah. So now can you stop sharing your screen and then we can see you now. So during your presentation, something happened and just something happened with the sound and the microphone just got killed. Oh. So now we have to share, Alberto and I, one of the mics.
Mic, yeah.
Okay. Yes. Then now it's time for the questions. I think that I'm super impressed of your presentation. It's impressive. The way that you have presented is excellent. So very, very clear, everything. Also the results that you have presented, awesome. And even gone the extra mile because all those things about, for example, controlling with the phone, this is extra mile, that's impressive. Another thing is capturing the cup back when the customer hasn't paid. That's awesome. That's very creative, very good idea, very funny idea, but also it's impressive that you decided to implement and it worked also. And also would like to say about the moment where the things they didn't work, but instead of panicking, you reacted very well. You identify where is the problem, you launch it again, easily going step by step, excellent reaction. And then everything ended well. So congratulations, Naveen.
Thank you so much. Because in production, this happens, right? Like it's not always the perfect thing. Sometimes the issues happen, so we need to react fast and do solve it. Learn from the construct.
Yeah. Really amazing work. So I want to ask the crowd, if now is the moment, if you want to make any questions, place them in the chat of the stream.
And go YouTube, right?
YouTube. Yeah, exactly. So I'm going to start myself picking one question from Rodrigo, and I'm also going to add mine as well. So Rodrigo's asking, can you explain a little more how you used the neural network to then connect to the coordinates sent to move it? And I also wanted to ask, this neural network algorithm, did you pick it from somewhere, or
pick a lead? Okay, so basically, let me share my screen, so because I'll be able to show the code if you like, maybe.
Yeah, go ahead.
Yeah. So, so basically, this is my neural network, which I trained on Google Colab. So yes, so first what I did was, I'll explain it step by step. Okay, so I got around 50 images, but this is very less. Just for the prototype, I got only 50 images, but for the production, we need like thousands of images. So what I did is I captured all the the bounding box values manually. I had to manually enter all these values and compute it, and then I stored it in a CSV file. Okay. So based on this is a image loader, image and annotation loader. That is the image as well as the bounding box value loaders. Okay. So based on this, I used a neural network that is convolution 2D with 32 filters and 3x3 kernel. And this is the input size, input shape of the image. Okay. So based on this, I was able to train the images, and then I got my training accuracy here. Accuracy, this is a regression task, so we're not going to use accuracy. So the loss, mean square error loss, is just 3.69, which is very less, but it can be below 1 if used multiple images. So how I got this idea is, once my gazebo algorithm failed, because I thought gazebo algorithm is going to work on real robot, but gazebo is like ideal algorithm, the black background at the back, so my contours worked. But here in my real world algorithm, it's noisy, and I don't have just the cup there. It has so many objects, so this did not work. So I thought, okay, let me take this step and train this neural network. So if you wanted to know more about neural networks, I'm using convolution 2D, max pooling 2D, and these are all layers of neural network. And I'm going to show you how this also works. These are filters. These are the 32 filters which the neural network are trained on based on my images. And based on these images, it's going to generate the smaller, I hope you can see this, Control K. Okay, I'm going to get these 32 images based on the layer 0. Similarly, there are multiple layers and there are multiple parameters. There's like 12 million parameters which were trained on the neural network. So based on these parameters, I'm able to get the bounding box values. And from the bounding box, I get the centroid, and goes on so forth.
Really cool. So, for instance, if we decide to change the cup for another model, which is newer, it would be just a matter of training the neural network, providing new images of the new cube, and that basically would be it, right?
Exactly. That's the same thing. You need to train the images with the cube, and then once your convolution network is ready, that's it. It's gonna, in seconds, you're gonna get the output.
And what about the position of the cup? Because you mentioned that it's been trained in a very close region, right? So
Yeah.
what would be the problem of putting the cup in another position for your system right now?
Right now in my system, it might not work because I have trained across the X position and few centimeters away from the X position. Because and if it's for the production task, we will train it across the table with multiple images. I just took 50 images. So that is actually not enough, but it's enough for the prototype, for the project to be able to show a demo. But for the production purpose, we need it across the table, multiple images, so that the training accuracy and the loss is very minimal, and we're going to get output with much higher precision.
Okay, yeah. So that's the ultimate goal of that
Yes.
project, which is to train the system to detect the cup in different areas of the whole table, not just in the cross, because it could be that the cup is put there with some imprecision from the previous stage, which is the stage you didn't show, but there is a stage previous to that you have used, which is to grab the cup from the cup dispenser and put it there at the position, right?
Yes, exactly.
Yes. So that's not included into your project. So that was just
An extra thing.
yeah, exactly. It was not included, but for the audience, I'm explaining so they can understand. Then maybe this process leaves the cup in a very different position for whatever the reason, for errors in the movement and so on. So a system that wants to be into production needs to have this possibility to detect the cup in any position. But that's very good in your case. So that would need a lot more of training images in the different positions and locations to identify the size and based on these size, understand where is the position.
Exactly. You're right.
So then what are you using the point cloud for?
Right now, I'm not using the point cloud. I'm just using the RGB image and the depth image. But due to the bandwidth, every time we'll not get access to the point cloud, right? Remote access to the point cloud because it's huge in size and we'll not be able to process it all the time. So I wanted to create an algorithm with minimal resources as the RGB image and depth image, and then use a convolutional network here.
Yeah, that's a clever solution. And also, I wanted to ask, because that I didn't understand very well. So at the second part, once you already picked the cup and you want to place it on top of the barista, so that part is not using perception, right? So that is just using regular joint position goals.
Exactly, joint position goals, exactly.
And you are going first to the ROS logo, and then you move from there to the cup holder, right?
Yes, exactly.
And that is for some particular reason, or?
I wanted to implement, once I go to the sticker, I want to select the holes. So from the sticker, I wanted to go 0, hole 1, hole 2, like that. I wanted to do that, but for this project, I thought, okay, let me focus on hole 0 and place it here. For future enhancement, I'll be able to, from the sticker, it's just few Cartesian movements, right? So I thought sticker is the main objective, and from there, I'll use a joint state goal to all the 4 holes. That'll be a future enhancement of the project.
Okay. Yeah, and you can even add perception so that you detect the ROS logo and then go there, for instance.
Exactly, yeah. That'll be great.
Okay, so let me look for more questions. Okay, I think that Girish's question is already answered. Okay, then for the trajectory planning,
yes,
you are using the regular planner, KDL, the default one for Movie 2?
Yes, KDL IK I'm using, yeah.
Okay, and did you find there any problems with the trajectories generated?
Here, as far as this is concerned, I did not find any problem with KDL. I thought of going to LMA, but that was my second option. But KDL, I did not find any issues. And even in OMPL, I did not find any issues. So I just stuck with the default planners and plugins. Yeah.
Okay.
Yes.
Okay.
Because what matters here is the collision objects. Here, in our case, we have minimal collision objects, and it is possible for KDL to execute make the trajectories. So it was good with KDL.
One question about the cup detector is, why did you decide to create this neural network instead of using something like already exists, like YOLO, for example?
Okay. So first thing is, I wanted a hands-on experience because using YOLO, VGG, RGG, ResNet and all, this is very common. Everyone uses a pre-trained network and just, it's very common. I wanted to have a hands-on experience to code from scratch. So because I know my task, because when I use a pre-trained network, it's going to take a lot of time for me to detect the cup, and I need to go, I can't say my objective. What's my objective? Detecting the cup. I can communicate it with very clearly to RGG or something, because pre-trained network are trained on multiple images, so many images on the web. But my neural network will be trained only on the cup image and not anything else. So my focus task is going to be very clear. Objective is very clear there. So I wanted to use my own Scratch network.
And did you try with different light conditions?
Light
conditions. So
lightning. Okay.
Yes.
Okay. No, I did not get a really lot of time to experiment with this. So I wanted to do this. This actually should be done, because there can be different lighting conditions, and our predictor cannot, get fooled because of this. So we need to do this actually.
Yeah, in the case of our cafeteria, that was not required because the cafeteria is inside, so it's not dependent on external lights. So only has the lights of the ceiling and the around, and more or less they are stable, more or less, most of the time. So that works. And also there is no people in there. When you are doing all this training and all these tests, there are no people that can occlude the lights and change the light conditions for the cap. So it's not necessary. But it's true that for a real cafeteria, that will be required to train under different light conditions.
Yes, exactly.
Okay.
In case if the ring light fails or something, that time, yes.
Exactly. Okay, then, so in order to finish, so what would be the part that you consider the most difficult of the project?
Most difficult one was the perception, because it sounds easy, like, you have the image here, RGB image, depth image, but when I solved each and every problem, I had another problem. When I got the centroid on the RGB image, then I realized, oh my God, the dimension of the RGB image and the depth image is different, right? So I wanted to do an offset there. So I had problems coming up. The trajectories was very easy. Everything was easy, but the perception was very difficult, but somehow managed it. Yes.
Okay, so yeah, I think we can leave it here. Thanks a lot for your presentation, Naveen. And
yes, excellent presentation and excellent project. Naveen, awesome.
Thank you so much. And first of all, I would like to thank Mr. Ricardo and Alberto for helping me throughout the masterclass and the project. And special thanks to Mr. Girish and Rodrigo.
Yes,
because
those
not,
they are
oh
doing
my
the heavy work. They too.
I can't imagine doing the project and the class. So thanks to all the four of you and for having me here.
Thank you for your dedication. This is the kind of students that we want in our masterclass. So thank you, Naveen. And congratulations for your title. Well deserved. Congratulations.
Thank you so much. Yeah, thank you. Okay.
bye-bye. All right, so we are going to get started in some minutes with the next presentation, which is going to be performed by Jēkabs Jaunslavietis, and it's about autonomous trash table picker robot. So should we go already with that, or maybe we can have some pause of some minutes?
No, I think we should go.
We should go for that? Yeah. Okay, then let me...
So, in the meantime, we are waiting for who is the next student?
Jēkabs.
Jēkabs. Okay, Jēkabs. Okay, so Jēkabs, we are calling Jēkabs now to attend the presentation room. And he's going to be talking about
autonomous trash table picker robot. So basically, the project is going to be based on a mobile robot. Also, he's going to be connecting here to a real lab that we have here at our facilities in the construct. And basically, the task is also based on the cafeteria that Naveen has presented to us, but not on the arm side. So not on the coffee side, but it's going to be a robot which is in charge of cleaning the tables of the cafeteria. So, yeah, then we are going to be seeing another side of an autonomous cafeteria. So, yeah, I think that we already have Jēkabs here. So, let me try to switch to Jēkabs' screen in a moment. There we go. Hello, Jēkabs. Can you turn on your camera? There we go. We can see you.
Hi, can you hear me as well?
We can hear you, Jēkabs. Yes.
Okay, nice. Just a second. I will try to share my screen now, right?
Yeah. So if you want to go...
Okay, can you see it?
Yes. Yes, we can see it, Jēkabs.
Okay, then can I start? Or...
Yeah, go ahead.
Okay,
All yours.
Yeah. So I'm going to start with this picture. You know, what is one of the most boring tasks in my life? I'm going to give you a hint in this picture. You know, there is always full trash can which I need to bring outside to the container, and sometimes I need to do it like 2 times per day, or sometimes 3 times per day. And once I got as well depression, and then at that moment I decided that maybe we can actually automatize this task, right? Because there are like many robots nowadays. So maybe we can use some real robots to solve this real problem, which is really important for me. So that's why I'm going to present like trash table picker robot by me, Jēkabs. So let's continue. What is trash table? Most of you are thinking no, right? Is this trash table? It is kinda, yes, but not for this project. When I say trash table in this project, what I mean, it is table, it has 4 legs, and there's trash can on it. To be honest, it is not really important what is on the table in this project, but to give it some meaning, and it would be easier to find idea, it is called trash table. So the problem description. The main goal of this project was to develop autonomous system for a robot which can localize itself in a space. It can do path planning, localization, and find these trash tables in a room and bring it to another room here and drop it down. So step by step, for example, to better understand here is robot. He's able to do localization and path planning. So he navigates in a room, he finds a table, he goes under the table, lifts it up, and then automatically goes to the back room where it lifts down the table, and the robot goes back to the main room and continue or waiting for another orders to search for another table. So I hope it is clear. Main tasks to solve the problem. These tasks were given from my mentor, Rodrigo. So I will go one by one, and I will explain how I solved them and what kind of problems I got. There is one task which I will not going to mention. It is containerizing project, because there is some technical problems with Docker. So I didn't do that one. But if you have some questions, we can later discuss about that. So number 1 task was to make localization working for a robot. I will not go very deep because I used ready-made solutions. I didn't write my own plugins, but I used like standard adaptive Monte Carlo localization, like standard planner, which is Dijkstra planner. But I want to say that for a controller, I used rotation shim controller. As you can see, here is a GIF in bottom of the slide. And and it solves a really big problem. When there's a goal right behind the robot, using only DVB local planner, it was really hard for me to actually do path planning, because it kind of stuck and it couldn't turn to the path. And at the beginning, I used my own like kind of controller. I tried to rotate to the goal pose before actually starting to execute this path. But at one moment, I found out that actually ROS2 has already this implemented called rotation shim controller, and which uses actually DVB local planner as primary controller. That was number 1 task. Then trash table detection. It was one of the main tasks in this project. So how I did it? At first, I want to say that it was based only on laser data, not on intensities values, but on like real measurements. Yeah, I hope it's clear. And so the first was filtering by distance. And the second one, I split them in groups based on like a distance between two points. If there is some bigger distance, then I assume that this is already a next group. So the third step was to remove small groups, basically because it might be noise. And the last step was I filter groups by shape. Basically, I measured what is the distance between the beginning of group and at the end of group, and I also measured deviation in the group. And if it was too big, I just dropped it because I knew the table like dimension. And then I approximated this group to the point by distance and angle, like in polar coordinates, and then that's it. And then I used a little bit of math to calculate distances between these groups and try to find table pattern. Here is visualization. As you can see here, what I want to say is that I used TFs for publishing a table because it's really, really useful. At the beginning, I didn't use TFs, and it was really hard to actually visualize the table. Yeah, as you can see, for every leg, I have TF frame, and they are sorted by the distance to the robot. For example, this is the closest leg, and this image, the closest leg is the right leg. I will explain in the next slide why it is important. Oh, no, not in this slide, but afterwards. But what kind of problem I got here? As you can see, here is a table. In real life, on the right side, there is a visualization, and as you can see, here is table detected 1, 2, 3, 4 legs, but the actual table is actually here: 1 leg, 2 leg, the third leg, and the fourth leg. And in this point, my filtering worked almost perfectly because. But the problem was that it was as the lasers can start to scan from like this side, and it found some chair legs which are very, very similar, and I couldn't actually distinguish between table, a real table, and fake table. So that's what I did. I tried. So I made a keep out zones in my map. That, for example, if there is table in that zone, I don't care if it is a real table or it is not real table. I'm not going to approach it because it might be dangerous or it might be not a real table. So that was my solution for such a problem. About approaching a table, actually, it was also a little bit hard task because I need to know orientation for table, because I need to know where is the front of the table. So that's why I sorted legs by distance. So I assumed that this was the closest legs. So I published another frame between the 2 closest legs, and I assumed that this is the front of table, and I published 2 more frames. One is pre-table frame. So robot needs to navigate to the pre-table frame. So I can be sure that robot doesn't hit table legs. And then there is a back table frame, which is the last frame where robot should go. And here is a small demonstration. As you can see, the robot goes to the pre-table frame here. So it is not important how table is oriented, because he will always find the front of the table, and then it rotates to the back table frame. It is right in middle between these 2 legs, and then it goes until there is some constant distance to the back table frame. Yes, that's. I will also show you, of course, in real demonstration as well. And for web page, I used Foxglove. I want to mention that I'm not sponsored by Foxglove, but it is really cool tool to use. So maybe I'm kind of cheated because I didn't make Foxglove myself, but it is really easy to start with Foxglove because it is already a containerized tool. So basically, it is like I need to only make my own layout. As you can see, here is setting tab. Here is a 3D space where you can publish any topic you want, like images, maps, cost maps, laser scan data. So I made here teleoptimist like controller. Then there are some topic publishers. This is log from ROS, which is also very useful, that you can see everything what happens in your ROS system, and there are like 2 service calls. Yeah, and what basically this is like web RVs. If you have this Foxglove, you don't actually need any more RVs because you can see everything what happens, and it's really useful for debugging and safety because you can see where is your robot and on a map and so on. And about project structure, before I'm going to show a real demo, it is it is pretty simple. Here's navigation part, and then I have like two nodes. My main node, which communicates with nav2, which says go to that point, go to that point. There's table node, which is responsible about publishing, very stable, and also about approaching table. Like there's action server, and there's a Foxglove bridge, which is used for web page. I want to mention that it is not important if I use Foxglove bridge or ROS bridge. Foxglove can use both of these bridges, but in my case, I use Foxglove bridge because Foxglove says that it has better performance for large data. Okay, now it's time for the demo on the real robot. Let me give some minutes to actually connect to the real robot and launch everything.
Well, now it's the moment of truth.
Hopefully it'll work. As my project is not containerized, I'm going to launch it manually. I have 3 scripts. I could also do it in 1 script, but for safety reasons, that it would be easier to restart if something goes wrong. I made it in 3 scripts. This is for fast planning. Sometimes takes some time to start actually. So. This is for table detection. This is for ROS bridge. Okay. And here is as well, I need to launch my web page. Oh. And now I need to initialize a robot position, but I need to find where is actually a robot. So. This is a real robot. Okay, I'm going to initialize a position. I'm going to drive a bit, so it's better localize itself. As you can see, my web page actually works. I can drive my robot. For example, I go to the back here, and there are 2 service calls. One is for approaching trash table and bringing to the backside of room. So I press call service. As you can see here, it was called, and here is a web page. You can actually also see a plan of the robot. Here, it's the same as an Aris, but I will use my web page to show actually how cool is Foxglove. And right now it is just going to one point to another point, and during it goes, it also checks for a table all the time. And when it will find the table, let's wait until it finds, hopefully. And as you can see, right now he found a table. He published some frames. It is kind of messy because of frame names, but he's doing what I showed previously. He went to the front of the table. He went under it, and then he lifts it up. He moves back a bit, so it is, in case there is like closed obstacles in front of the table, it doesn't hit when it rotates. And then it goes to the back room. There aren't any cameras in the back room, sadly, but there isn't happening anything interesting. Actually, it was this one is really critical part because the doors are very there isn't big tolerance for a robot actually to go between doors. So yeah, it was a bit of controller tuning until it actually succeeded before hitting. And here in this process, he left the table, then he goes back, and the robot goes to his home position, which is around this point. This is the most boring part. It just follows the path until it gets home. And but as you can see here, the process is still going on, and we are waiting for answer. But while it's going, I can say one drawback about Foxglove, which I don't like personally. The problem is that it cannot use ROS2 actions at all. So I need to make service call, which has some limits. For example, I cannot cancel service call, as far as I know. And I can get a feedback. I don't know in which state the robot is right now. That is a drawback. So this is service call. And while we are, as we can see, here's the status of our service call. It is robot delivered table and got back home. Like that's what I expected. So maybe Rodrigo can you please put table in some random position, maybe, so it is oriented differently. Yes, but it should be on where camera can see the table, because it just searches for that space.
Let's see if Rodrigo can get your.
Yeah, he's going there.
Yeah.
You can see
cool.
there in the cameras.
Now it's put in another location, in another orientation.
Okay.
Yeah, and we can see with both cameras.
Yeah, it's cool. I'm going to call again this approaching the table. As you can see, there are some bugs actually in Foxglove. Here's it. You can see they are like frames. They are not real frames, because on Aris you don't see them. Actually, you see, it is a bug in Foxglove, so it is not perfect as well. There is a distance limit, I think, if I'm not wrong, around 1.5 meters until it actually using these laser scans to look for table for safety reasons, because once it detects table and goes under it, it doesn't actually check for obstacles anymore. And if it might be a problem for real life. If, for example, if there is some brick under the table or in front of the table, it would crash. Yes, and seems it detected table again. So he again published table frame in front of the table, which allows to approach table, not caring about table orientation or where it is. And now it's happening the same. Actually, it is going to fixed point in this room, so it also might be a problem for a real like for real life, because if there is something in this target point, it would fail. But I will leave it for maybe future students to solve this problem. As you can see, a camera here is stable. Let's wait for robot to come back.
Yeah, so inside that room, we are hiding some secrets from the construct, so we cannot show it. Sorry for that.
Yes, but we can still find these secrets by laser scan, because we can see everything on my webpage, right? That's why it's so cool.
Yeah, that's true. Yeah.
Maybe to save some time, I'm going to cancel this service call. I'm going to publish here, to go here. So it will not go home. So it's faster. What I can try, I can actually call the second service call to go after the table. For example, we assume that this trash can is emptied. Okay, and actually there's like status message, robot lost his way back to home. So on a web page, we can actually see the table is delivered, but we can see that something happens actually going back home. But okay, let's see. Let's call bring trash table back to the main room. As you can see, it published here a path. The process is very similar, because if filtering works, then it can find table in any space where you want. So it is not really important where is this table. So it went to the back room, and then it starts to search for table starting from this point when he enters in that room. Because if there is a task bring table back, then it's important that it only finds table in the back room.
We really should have put another camera there. So I can imagine how difficult it was for you to test this when something went wrong on the back of the area, right?
Yes, but to be honest, when I only implemented this step as a last step, because when I knew that everything works, and
Okay.
I just actually this trying to go after the table, I didn't try too many times. So yes, but I hope it will work.
Okay, very clever. Oh no, he's coming.
Yes, yes. there is some problem in a navigation stack. It is not like problem it is problem in my code that there is a like progress checker, and if it goes under the table and it rotates very slowly, and then it kind of detects that there is no progress in executing path, and then it makes some recovery behaviors. But as you can see, it went back, but right now it did some behaviors, and it is working again. So it works.
Yeah, there it comes with the table.
Okay, let's switch to camera. Yeah. Oh, this was very close to that side.
Yeah.
Too close, but it worked.
In the nick of space.
And yeah, as a footprint, I use fixed footprint. I don't change footprint during my mission execution for simplicity, because yeah.
But then
because
which footprint do you use?
What do you mean, which footprint?
Yeah, so do you use the size of the robot as a footprint? Or
no, I use the size of table.
Okay, so for all navigation, during the whole navigation process, either the robot is carrying the table or not, you are using the table footprint.
Yes. Because it might be possible that I don't know if there is table on the robot, right? It might be possible that if it stacks or yeah. So and also it was easier for me. Now it is dancing. I think he's trying to approach local goal, and it kind of okay. But you see, great job here. Great job. He finished his task bringing back table, so I can also publish down elevator. You see, it went down, and then I can drive my robot from my web page. So yeah, this was a real demo. I can show you one more time, or we can also leave some time for questions and answers. It's up to you.
Yeah, I think we can go for the questions and answers.
Okay, but I'm going to present one more slide.
Sure.
Because I have time.
Sure.
Okay. About conclusion, there are of course some improvements. One is code cleaning. My code is right now a bit dirty because I didn't have time for that one. Who cares, right? And then the second was table detection. Right now there's like table publisher, which publishes only one table. But if it is a fake table, then we will not find the real one. So what I would suggest, and if I could, I would improve. Actually, I publish all the tables which I can detect, and there would be like table approacher, which would filter which one is the real table. For example, which is in a keep-out zone, so it is not a real table. And then it could also like find a real one, or the best one he can approach, which is closer to the robot. So yeah, this is the second point. And the third one, which was really, I mean, how it started. At the beginning, there was simulation from Rodrigo, and I kind of struggled because in simulation, there was table right next to the wall, and it was really hard to in Lidar data to detect which is wall, which is table. So I spent a lot of time trying to do this small task, which is an edge case, and it might actually not even happen in real life. So in one day, I told Rodrigo, so I'm making my own rules. I will move table to the middle of room. I will change size. I will make it bigger. I will make the table like symmetric. And he was like, of course you can do it. You are an engineer. And so this kind of rules, when I don't think about edge cases, but only trying to focus on a real problem, it really increases the performance and speed how I solve the main problem. And then actually I have more time to actually solve these small edge cases. Yeah, and that's what that is from me the main how to say it in English. Yeah.
Like you decide your own conditions.
Yeah, I mean, it is not it is not possible always, of course, to make your own rules, but in a software development, you need to make some assumptions to move forward. And yes, and it is better to solve main goals than trying to solve some small edge case, which maybe is unsolvable. So yeah, that is from me. Thank you, of course, Rodrigo, for my mentor and the construct team. And yeah, you did a great job. I really learned a lot, and that's from me.
Excellent.
Great presentation, Jēkabs. Thanks. So let's go with some questions. If anybody in the audience has questions, please write them in the YouTube chat. So let's start with some questions by your tutor, who of course knows the project very well. Then Rodrigo, for instance, he's asking, once the robot goes underneath the table, how did you manage the disappearing front leg frames? Are they not needed for your approach algorithm?
Yeah, this is a really good question. I have a timeout for all legs, 15 seconds. So in case approaching takes longer than 15 seconds, it fails. So, and what I do when I look for table legs, I look table legs relative to odometry frame, but as a fixed frame, I used map frame because odometry frame is changing because of navigation stack. So there is some function which allows to do that. So yeah, basically, I don't use front legs when I don't see them. So as I have 15 seconds timeout, but when I see all the four legs, I published all the frames I can. So when I don't see the front legs, I just use the last known position of table. So of course, if the table would move, someone would move table position during approaching, I would fail. Yes.
Okay, you mentioned something is interesting for me is that you are publishing the frames related to the map frame.
No,
right?
I'm publishing relative to laser sensor, but when I'm
okay. Now that makes sense.
Yeah.
Okay, so I understood that was from map frame. So what did you publish from map frame then?
No. When I subscribe these frames, I subscribed relative to odometry frame, but there's like extra parameters that I actually measuring against map frame. But it was like when I subscribed, not when published. When I published relative to sensor frame.
Exactly, because you need to approach related to the robot,
yes,
to the current position of the robot, to the robot center itself.
Yes,
not to some.
But there is problem. For example, if I subscribe as in odometry frame, it might be that adaptive Monte Carlo localization node switches odometry frame, right?
Yes.
True.
Yes.
And,
switches from one
and
place
that's
to
why
another.
I used this like transform between odometry to table, but I considering that map frame is a fixed frame. So yes.
Okay, then I have a problem with understanding. I didn't understand if you are using navigation for both things. First, to figure out where is the table, and second, to get underneath the table. So getting underneath the table, are you using navigation also?
No.
Okay. Can you explain?
No.
How did you get... so can you explain the two different, let's say, navigation modes that you are using?
Yes, sure. So when I'm going in a space, when I'm going to one point, another point, I'm using navigation stack. But once I detect table, in that moment, I stop navigation task, and there is a proportional controller, which basically I subscribe to table frame, and then I measure distance and angle, and that's it. Yeah.
Okay, excellent. That's what I wanted you to clarify, especially to the audience, because many students have this problem. They learn about navigation, and then they think that they can use navigation for everything. But there are some tasks of autonomous movement, that where navigation doesn't apply because of the precision or because other problems, like getting underneath the table and getting occluded some things. So that's one of the cases, right? And then how do you manage the occlusion of the legs of the table?
Can you repeat your question?
Yes. So once the robot is underneath the table, it's carrying the table, then the lidar is detecting the legs, right?
Yes, but when I'm moving, I don't care about legs anymore.
Why not?
In that moment, for simplicity, I assume that table is not moving when it's on the robot.
Yes, I mean those legs are causing on the lidar the detection of an obstacle, which is just in front of the robot, right?
Oh no, I use extra parameters that there is like minimum distance for local as well for localization. There is minimum distance which is not considered, and also for cost map there is minimum distance which I don't consider as an obstacle. So it's solved.
Okay.
Yes.
Okay. Yeah. I'm asking you about just to see that you have clear those concepts and very well.
Yes.
You passed.
Oh, nice.
So even after carrying the table, at that moment it is doing dynamic obstacle avoidance, because I think I understood that it's not, or.
No. After it lifts table up and when it goes to the back room, of course it does obstacle avoidance because it uses navigation stack already.
Okay.
It is only going under the table. It is based on odometry, like local planning, not using navigation. But
Okay.
once it lifts it, it can avoid obstacles.
Okay, great.
Just that if there is an obstacle, so let's say we have the robot without carrying table, is doing navigation, okay, trying to find the table, let's say. And then there is an obstacle, like a person that comes into a position at a similar distance than the legs would be on the robot. They will be not detected as an obstacle, right? So I mean,
if those legs would be in front or right in front of the table, and if robot already would be approaching table, then no, it wouldn't be an obstacle, and robot would hit that human.
Obstacle. That human.
Yes.
Yeah. Okay.
So there are like a lot of improvements to do actually, and yes, I assume I make many rules as I said in conclusion to actually make it work. So
yes, but that's what you did is correct. So it's the way that we should work, because sometimes the engineering problem is too complex for the resources and the time that we have, and then we can simplify in some way. For example, you were explaining about the problems of detecting the legs and not confusing them with other things. Then how do we do this? Then we can do an artificial intelligence. Well, okay, yeah, you can put just a strap of reflectant tape on the legs of the table, and that's it. That will give you an intensity of 100 compared to the others that say 1, an intensity of 1, and the tables. And then by doing that simple thing, then you can detect one from the other. That was not your option right now, so you decided to do something else. What did you do? Can you explain us a little bit more about this mask that you decided to do?
Yes, I can also maybe switch to presentation or no.
Yeah, sure.
Okay, yeah. I will share my screen one more time. So I inspired from navigation stack because I also use keep-out zones, but it's really simple. As I said, there's like a table publisher which publish table, and there's a table approacher who listens to these frames, and he actually checks if any of these legs and also pre-table frame is in keep-out zone. If the table or if the pre-table frame or any of these legs are in this keep out zone, then it just skips that table and continue to navigate until it finds another table. Yes, and that's it. Of course, this keep out zone in my code, it's really simple because there is a map frame. So I made like a constant value. For example, if any of table legs are in a map frame, like more than like one meter in X or Y directions, then it is in keep out zone. And that's it. Is it clear or?
Yes. Then this solution works for that specific environment, right? It's tuned to that specific environment.
Yes, but I could make these keep out zones actually not only for that area, but I could also make for anywhere I want actually.
Yeah, I understand.
So the keep out zone, you are publishing it with code, or are you manually editing the map?
It's not no. It's not so complicated. I just when I subscribing to table TF frames, so I just measure in a map frame where they are located, and then I just check if this distance is in keep out zone or not. It is in my code when I'm subscribing these TF frames. So I measure considering map frame where it is.
Okay.
But it would be really cool if in the future if it would be possible to publish like keep out zone similar way as in the navigation stack. Yes.
Okay. Then I have another question. Is about once the robot leaves the table, then it depends on where is the robot positioned underneath the table, because if you don't get at the center of the table, then the rotation of the table can have a different shape rather than square, because if you are not at the center, the robot is not underneath the center of the table. So how did you manage that? Are you achieving to get into the center of the table when you start lifting it, or you have some tolerance and you are managing this in some way?
I think I managed to do it right in the center, because there is actually a robot diameter is I think 40 centimeters and distance between legs is 50 centimeters. So you should be almost in center actually to go under the table. Otherwise you would hit. And yes, I assumed that I am in the center, and I think it was pretty well.
Yeah. It looks like it's on the center. Yeah.
Of course, it might be that when I'm going to the back room, somebody hits the table, or it also like sleeps a little bit because of inertia. And when I'm lifting down the table, then it would be actually a great idea to check what is the position of table, because otherwise I could hit table legs when I'm going back from the table. So yeah.
Okay, because when you are back, you are just moving back.
It's true, and it might be dangerous.
Blindly. Okay.
Yeah.
Questions from the chat. What do we have?
We had one from Rodrigo. It's actually not a question, but more like a comment. He was saying, I heard some jerkiness on the robot after it drops the trash table in the back room, as if there was an interruption in the command bell publishing. Can you think of a reason why that would happen?
Happen what? Like
like an interruption in the command bell publishing. I don't know. Maybe it's not that. It's just a guess.
He talks about
what kind of publisher? I didn't get it. You said there was some interruption in which kind of publisher?
In the command bell, in the velocity, when you are publishing velocities to the command bell topic.
Yeah. I'm not sure.
Well, he says that once you have, if I understand correctly the question, because it's a little bit cryptic, it says after you dropped the trash table
in the back room,
in the rack room. Okay, so then I assume that now you are moving backwards blindly, and then he says that he has heard some jerkiness, like the robot, instead of going straight backwards, then it's kind of, yes, it's kind of doing a click, 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 going backwards. Any idea of? Okay.
I got an idea. It might be. I'm not sure what is the controller rate, like timeout rate in a controller for the real robot. It might be there is like this watchdog timer, or how it is called. That, for example, if there is no command received in some specific time, it might be that it stops the robot. And I think I'm publishing it with 100 milliseconds rate, and it might be that it is too slow. It might be that's the reason.
Okay, 100 millisecond it's okay. It shouldn't, but it could be. It's a possibility. It's a possibility. Yeah. Okay. In any case, your answer is very good. So it shows that. So those questions here are just to check that you know the material and that you are mastering all the material that you have been learning during the masterclass, and that's the purpose. Okay, so whatever it's that the reason, so you demonstrated that you understand what happens and so on. So very good. Do we have any more questions?
No, I think we can already leave it here for the presentation.
Excellent. Then just leave it here. Congratulations, Jēkabs, for your title.
Thank you. Okay, then thank you, and I'm yes. So, bye.
All right, Jēkabs. Bye. Okay, so we are going to get started with the next presentation. So let me already see if we can contact him. Next presentation is going to be delivered by Robert Gruberski. It's a very cool presentation, and this one is not actually based on one of our labs, like the two presentations that we've seen so far, and also the two that we are going to see after Robert's are all based in our real robot labs here in the construct. But this one, actually, it's not based in our labs, but it's based on a personal project, on a personal robot that Robert has been building for ROS2, and he is going to be explaining us the whole process of creating this ROS2 mobile robot, this ROS2-based mobile robot. So I think we already have Robert here with us. So let's see if we can see him and hear him properly. Let me switch here to...
Hello, Robert. How are you doing?
Yeah, can you hear me?
We can hear you, yes.
Barely, and we cannot see you.
Yeah, let me choose.
So, there it goes.
Should be okay.
Sound is a little bit weird. It's like sound is getting not through your main mic, but some other camera.
Like a bit distant, maybe.
Yeah, like some other cameras that you have there.
I don't know. Maybe now something better.
No.
No.
No. It's like, I know that you have several cameras there because you are going to show us. And then it looks like the sound is getting through there and not through your computer mic. Maybe it's on OBS.
One thing, maybe something better.
Yes.
Is it okay now?
No, it's the same. It's the same. Okay, let's give it some seconds to Robert, because I know that his sound is very well. We have tested before.
Maybe give me 1 minute. I will connect my external microphone. It should be better with that.
Headphones, okay, let's do it. Because then the people can understand better the sound. Sound is very important.
Girish is also saying here in the chat that voice is very low.
Yeah, we barely are listening to him. So let's give Robert a minute to bring his headphones. And in the meantime, you can see there an image of the robot that he's about to show us, that he has built using the knowledge that he has. Let's see.
It's okay now? Maybe.
Yes, much better. Yeah.
Okay,
much better.
cool. I think I have too many cameras connected to my computer and I don't know which one is connected as microphone. So yeah.
Yeah, very clear now. So yeah, it's all yours, Robert.
Thank you. So I want to share my journey about building robot from scratch, just from, let's say, nothing to fully operable robot. My main idea was to design robot which everyone can produce, everyone can print the chassis, buy some cheap components, build it as cheap robots possible to work with ROS2. Let me run the presentation. So, as I said, at the beginning was idea to create something easy to reproduce, something cheap, and something easy to program and develop. And after a while, it wasn't so simple as I assumed. There were many problems on the way, but maybe from the beginning, from the first step when I started work on the robot. First phase was design in Fusion 360 CAD software. I made the whole design with all elements, with all electronics, with all drivers. My main idea was to create one different thing. After I made a design in CAD software, I create the simulation in Gazebo Ignition, in new version of the Gazebo simulator. It was pretty easy because Fusion 360 has plugin for URDF generation, so I use it, and let me show you the simulation right now. Yeah, as you can see, the robot is pretty similar to the robot from design. It's URDF file generated from Fusion 360, and we can with ease use this robot in simulation. It's based on ROS2 control plugin. So the whole project is based on Docker containers, so we can run everything with just one command. I will show it you in a few minutes when we will run robot in the real environment. Now let me back to the presentation. So after the design phase, after the simulation, my next idea was to design on my own PCB controller with all elements on the single board. I did it. The PCB has been designed, has been produced. I received it from the production, from the PCBWay company with the whole assembly process. Everything was fine, but a few problems appeared. I had a few mistakes in the PCB design. I tried to repair them with some simple elements, as you can see, resistor or some cables, or some soldering on the PCB. It wasn't possible to fix all mistakes made on the board, so it is necessary to create second revision. I have been working on it, and I think this board should be ready in the next few weeks. Then I will share more information about the PCB. When PCB was wrong, I had to change my plans and use different elements. So the first idea was to use market available RIDI controller with STM32 microcontroller on the board. So I used DF Robot DC motor driver hat for Raspberry, but my idea was to change the internal software of the STM32. I did it. It worked, but after some tests with Raspberry Pi, with communication, I figured that I2C communication wasn't so stable, and I couldn't use it with the project. So I had to change the hardware one more time. Then I decided to use simple controller driven by PWM signal with the external MCU board. I choose Tensy 4.1 board to this project, and create embedded software for encoders reading and motors driving. When I had all the hardware available on my desk, then I had to make some hardware architecture of the robot, and I split it into a few parts. One was the main brain of the robot. It is Raspberry Pi version 5. Then the embedded part with Tensy 4.1 board to motors driving and encoders reading. This is connected to Raspberry Pi by UART, and the whole software on the board is wrote by me. The board has PID controller and all elements like power delivery and things like that. The next element of the system is next Tensy board with Ethernet add-on. And this one has Zeno Pico on the board, some kind of DDS system which can communicate with Zeno DDS on the robot and on the server. A little bit more about it in a moment. And Raspberry Pi, a part of the elements, has camera and Lidar. I couldn't use both at the same time because of some issues with USB. When I tried to connect RP Lidar to Raspberry Pi, my camera crashed, and I don't have any idea how can I fix it at the moment, so I didn't want to spend more time on it, and I just stopped on the camera. After the hardware part, I moved to the software part. And I decided to use ROS2 with Zeno ROS2 DDS plugin on the Raspberry Pi, and everything is placed in Docker containers. Thanks to that, we can run everything in just one command, and with ease reproduce on almost every single board computer or Raspberry Pi. What we need is access to serial ports to communicate by UART with embedded system and connection to the internet. We don't need anything else. This is internal communication diagram of the whole system. We have central Raspberry computer, as I said, connected by UART with Tennessee 4.1 board, which has PID control on the board as closed loop. The board is responsible for reading the encoder signals and driving the motors by PWM. On the other side, we have the same board, the same Raspberry Pi Tennessee board 4.1, but with the Ethernet add-on. And this one is responsible for communication with remote systems. Only one element that I have connected at this moment is IMU ICM 20948. So we can read IMU messages from the module by XenoPico into Raspberry Pi. One of the hardest part of that system was to create my own implementation of ROS messages serialization, because it's not available for XenoPico, it's available for MicroROS. I couldn't use it, so I had to write it as my own. It based on Arduino. I tried to use Zephyr RTOS with my own board and STM32 microcontroller, but because of problems with I2C communication, I couldn't use it. I had to change the framework for Arduino, and now all the both sides, embedded sides with the motors and embedded sides with XenoPico, are based on the Arduino. I will expand it in the future for Zephyr RTOS, but first I have to receive a second revision of my board. The important element of the whole robot is external communication with the cloud. On the robot, we have XenoROS2 DDS plugin, which can automatically connect with Xeno router in the cloud, and thanks to that, we can exchange messages in both sides. We can read every topics, every data from the robot. Also, we can communicate with the robot by sending the data like velocity commands. At this moment, this is only one functionality that is available. We can teleoperate the robot from every localization around the world by the web interface, which I show you in a moment. Yeah, this is the time when I can show you how to run and how to work with the real robot. Let me. Oh, this page, yeah. Let's start with the terminal. Here, I have SSH session with the robot. In the workspace, Docker Compose file is available. And we can run all containers just with one command. There are containers for camera streaming, for ROS2 project, and for ROS2 DDS client. I don't have auto start of ROS2 nodes because I want to show how to do it. Let me access to the container. Okay, I have to make one change in graphical interface, and then we can run the robot just with one command. As you can see, we have visualization of the robot in Arvis, and we have a remote view of the camera in web interface. Also, we can access to the joystick, and we can operate with the robot just by...
So this is live, right, Robert?
Yes, yes, it's everything live.
Actually, it can show. It can. The robot can see you, right, over there.
Yeah. Let me. Yeah, I'm here. And the whole communication is made by the cloud. Web interface is on my local computer. It uses REST API on the VPS server in the internet, and by the Zeno network, it communicates with the robot by sending teleoperation command, by sending the velocity commands. And now it's everything what I have in the physical robot. There is a lot of space to expand functionalities with new sensors, new elements, new communication, new web parts. Let me maybe back to my presentation. I have 2 more slides. The one very important slide that I have is that the whole project is open source. I will share it on the GitHub in the next week. Probably I have to fix a few things, make some polishes. After that, I will share it as open source, open hardware projects that everyone will be able to download the files, print elements in 3D, run the software in Docker containers, and build these robots in just few easy steps. Additionally, if someone wants to contribute and work on the project with me, it would be nice. I hope it will be nice open source platform to play with ROS, to learn ROS, and to expand knowledge about the ROS2 and robotics. So that's everything. What I prepared for today. My real presentation was quick, but possibilities of the robot are pretty simple. It's open for new functionalities.
Okay, excellent.
I'm a little bit stressed, so sorry for that.
No worries, no worries. Okay, excellent. Now then it's time for the questions.
Yeah, actually, we have many questions for
Cool.
you, Robert.
Yes.
So, from the audience, actually. So, yeah, let's.
I want to start with one that is quite interesting. So you have mentioned that you have decided to use Xenopico in your project. And then the question, there are two questions there. So why do you want to use that much problems by using this Xenopico and not just going and doing simple controllers with an Arduino board? And also, why to use Xenopico instead of MicroROS?
Xenopico instead of MicroROS because of the whole Xeno stack. There is available Xenopico for microcontroller. There is available XenoROS2 DDS for the robot side, for the ROS. And there is Xeno router that we can use in the cloud. So we have the whole complete stack that we can use to exchange messages from the embedded systems through the robot up to the cloud when we can share the video streaming, comments, and things like that. We have everything in the one complete stack.
Okay, but why instead? I think that MicroROS has also all those things, right?
If I know well, there is not the part for the cloud. We have only connection with ROS, with ROS2, with the robot, but there is no some external part with the cloud, some I mean the word.
I see. Yeah, yeah. To
Some
use
distributed
internet.
part of the system that we can expand with different nodes. So with Xeno, we can use many different robots in one stack. We can connect many domains, many robots, many remote localizations. We can work like in the VPN network, but with without bandwidth limitations, with really powerful and full speed communication.
Yeah, so me personally, I did not understand very well this Xenopico part. So can you explain exactly what is it doing, this?
This is Xeno for microcontrollers. We can use it on the embedded boards, on the small microcontroller, and share messages from this cheap, less powerful boards with the robot. This is pretty the same like MicroROS, but from the Xeno stack.
Mm-hmm. Okay.
Questions.
Yeah.
The problem we have here is to select the question because so many. I don't know. So without any order. So Andres Leonardo is asking, which libraries allow you to interface ROS2 and Arduino?
Which question was about libraries?
Yes.
There is no libraries. There is not too much libraries, to be honest, because this is simple UART communication. I made it myself. This is just sending the serialized extracts from pure C language. That I can rebuild on the robot side. There is no library for it. This is just Arduino with simple serial communication and simple serialization.
Okay, so that would be the libraries for serialization and communication with
no.
No?
It's the whole code on the Arduino side is made by me.
Okay.
There was library on the Xenopico side for IMU module. It is a library for SparkFun, which allows us to use digital motion processor that is available in the ICM device. Thanks to that, we can download quaternions directly from the ICM module. We don't have to perform any additional calculations. We have everything from the module.
Oh, awesome. Impressive. And then Rodrigo is asking about what do you think is the problem that prevents you from showing at the same time the Lidar and the camera?
Probably power limitations in USB of Raspberry, because I saw in logs some messages about high currents problems. RP Lidar, which I have in the project, is a very simple one, and it doesn't have external power source. It's powered by USB port,
directly,
the same as the camera. Both need some amount of the power, so I think this can be a problem to use both at the same time.
Okay, yeah, then let me recommend you a solution that maybe you can try for later, just to check if it is this. It says you can buy one of those USB hubs that have power, so that you can provide power, and then connect the USB hub to the USB of the Arduino, and then provide the power, and then connect into that hub. You connect the Lidar and the camera.
Yeah.
And then you will know for sure that they are fully powered.
There is different problem because I don't have enough space inside the robot to...
But just to do a test.
Yeah,
with the cables and see if that's a problem. Because if you have this problem, then you need to put some power control.
I can also cut the cords and deliver power directly into devices, because I have quite powerful power delivery module in the robot, but I didn't have time for it to make everything. As we agreed, I didn't have requirement about Lidar. I tried to add it as some additional part, but when I had some problems with power, I decided to stop it and run the project without it.
Okay.
Yeah, there is a question from Jēkabs who says, did you use any ROS2 ready controller specifically for the motor?
I used ROS2 differential drive controller and made my own hardware interface for ROS2 control. I made my own ROS2 hardware interface based on my different project that I made a few months ago for the hoverboards motors.
And in that picture that you have right now, I can see that there are omnidirectional wheels. So is it currently available, or do you have plans to make it holonomic, or?
Yeah, wheels are interchangeable. We can use both. I have classic wheels and I have Omni wheels. There is some problems with my floor because it's
so the surface is very important for this kind of wheels.
Friction. And Omni wheels were really slicky on my floor, so I didn't use it. I couldn't use it, and I had to change it to wheels with rubber.
Yeah, but the controller part works, let's say, so you can send commands.
Yes. For ROS2 control, we have available two controllers for classic wheels and for Omni wheels. Yeah.
Okay. Really cool.
Another question from Rodrigo. So, did you experience any problem in remote communication while using Xenopico?
No.
Remote.
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 With Zenopico, only with camera stream. When I tried to send camera by Zeno, it was pretty slow. So I had to change it to WebRTC communication.
Okay, but when you say camera, you mean the image, not a point
Yes,
cloud.
yes, only image. The whole commands are sent by Zenostack.
Zenostack. Okay.
It's based mainly on the REST communication. We have REST API available in the browser, and we can send commands by REST API into Zeno router and then by the Zeno network directly into the robot. And I didn't experience any problems with this communication. I had robots run for 12 hours and the communication was pretty stable.
Awesome.
Yeah, Andres also asked, how long did the development of the robot take, more or less?
About a month, probably. As I said, I had many hardware-related problems. I tried to use my own PCB, then I tried to use Zephyr RTOS and STM32 microcontroller, then there were problems with I2C communication, so I had to change it to different hardware. So it was the hardest part to choose good hardware and to create good hardware solution and good hardware implementation that can work with Raspberry and with ROS. The part with Zephyr and with I2C, it worked well, but not with Raspberry computer. I2C communication after 5, maybe 10 minutes was interrupted by some kernel problems, and I couldn't use it anymore, so I had to figure it out to use something different, and I decided to use classic and stable UART communication. The communication is almost the same. Only the physical layer has changed.
Okay.
One final question from Rodrigo also. Let me see, what was this? Yeah. So you mentioned at some point in your presentation, you mentioned a container for ROS DDS client. What do you mean by that?
There is used ZenoROS2 DDS plugin, ZenoROS2 DDS bridge from Zenostack, and it is placed in separated container. I have 3 separated container, one for camera streaming, one for ROS2 project, and one for ROS2 DDS. There is Cyclone configuration made to communicate containers each other and exchange the messages. So the ROS2 container can exchange ROS2 messages with ROS2 DDS separated container, and then this container can exchange messages by the internet with Zenobridge.
Okay. Then the picture will be the robot computer, which is the Raspberry Pi. Then this is running ROS, right? With DDS, with Cyclone DDS.
Yes.
Yeah.
Cyclone. I don't have good slides for it, but yeah, it's something like that. We have Cyclone DDS on all sides. Cyclone is run in the cloud with the router, and Cyclone is run locally on the robot with the shared configuration for all the containers. And then I can exchange messages by the SHM memory internal in the robot.
Exactly. And then in the Wi-Fi, it's only transmitted is the part of Xeno, right? Xeno messages.
Yes, and camera streaming because it's separated.
Yeah, and exactly. It's camera streaming because it's the thing that you said that you separated because it was not working somehow, the transmission. Okay.
Because of low latency requirements for teleoperation. With pure Xeno communication with Z-Capture program offered by Xeno, it was pretty slow to use for teleoperation. The delay was too high to teleoperate.
Okay. So I think we can leave it here.
Yes.
We've had Robert already answer many questions. So yeah, thanks a lot, Robert, for your presentation.
Thank you very much, Robert. Excellent presentation. Congratulations for your title.
Thank you.
Masterclass. Congratulations. So and now it's time to go for the fourth presentation of
yeah, so we are going to go for the fourth presentation of the day. The title for the next presentation is Trash Table Detection Using Only Lidar Sensing. It's going to be delivered by Ritwik Rohan, and we are going to go back to our trash table environment with a mobile robot, and we are going back to the cafeteria. So we already have Ritwik here. Then let's say hello to Ritwik. Hello there.
Hi, Alberto. How are you?
Fine, thanks. How are you?
I'm good. So, shall I start?
Yes, audience is all yours. Okay, we can see your
Hold on.
your slides now.
Yeah. So, hey everyone. So I'll be talking about my project on trash table detection using only LiDAR sensing. So let's dive straight into what I aim to achieve. So what's the main goal of this project? It's like training our cleaner robot to be a smart janitor. Its main job is to find the trash table, pick it up, drop it in the back room where it can be cleared out. So for this project, in the simulated world, I have been practicing on RB1 robot in Gazebo within the Starbucks cafe environment. So now in the real environment, I'm putting my practice system into action on actual cleaner robot, which basically has a TurtleBot 4 base and a LiDAR sensor and an elevator on top. So hold on. Can you see the video clearly? Because I have some problem with
yes.
my...
Yeah,
okay.
We can see it.
Okay. So I want to show you a quick simulation of video that I ran in Gazebo environment. So this video basically captures the core goal of the project and provides a glimpse into the simulated world I'm working with. So here you can observe that the robot carefully approached the table. It'll go back and then drop it in the back room. As Jēkabs had already like shown this project, so I don't think this is necessary anymore, but just for anyone who's joining right now, so this is my project. So here you'll see that it goes to the back room and it drops it there. So this simulation serves a preview of what the cleaner robot aims to achieve in the real world scenario. But I know this looks pretty straightforward, but there's a catch here. So as I explained in the earlier slides, the main task here is to detect the trash table anywhere in the map. But the robot that I am using has no depth camera, no intensity LiDAR, which is basically highly used in any robotic industry for object detection. So the task becomes a little complicated here. So first things first, before I get into the intricacies of my LiDAR detection algorithms, let's go through the initial step. So here it's pretty basic, nothing to explain here. Like I've used AMCL localization, which quickly adjusts to the robot surrounding. I've used the conventional Dijkstra's algorithm and a simple DWB controller. So all in all, it's nothing out of the ordinary here. So I'll just jump right next to the next slide. So here comes the real challenge. So now finally, now let's dive into the real challenge, which is table detection using only 2D LiDAR. So the screenshot that you see is from the real Starbo environment. Here, what I'm trying to demonstrate is that the robot only sees the laser scans, and using this, it has to segregate trash cans from all the other objects that are there in the environment. So to solve this issue, I've used segmentation and clustering algorithms, which I'll be explaining in the upcoming slides. So to give you a basic idea, these laser scans are segmented into separate scans, which is basically composed of points, which is then clustered together to create a segment. So now let's understand how these LiDAR scans are separated into different segments. So firstly, scan topic is subscribed from the robot scan publisher. These scan messages are then converted to polar coordinates. So you can see the formula here. So basically, now we have all the coordinates for each scan range. Now, here's the crux of the algorithm. Now, the polar coordinates that we obtain of all these points that you see here, we have all the X and Y coordinates of all these points. Now, the crux of the algorithm is that here I'm checking the jump distance between two points, the point which is next to it and the next point. So basically, when if the jump distance is set to 0.2, that means if the distance between previous and the current point is less than 0.2, then it will be part of the same segment. If it is more than 0.2, that means it's part of different segments. So in this image that you can see, this let's consider this point is this distance is greater than 0.2. So it will be considered as two different segments here. So this will be one segment, this will be one segment, these whole will be one segment. And that depends on my jump distance threshold that I'm using. So this is the visualization of the segments that I'm going to show. This is what I started with. So at first, after using just the jump distance algorithm, I was getting all these segments. The cube that you see is the centroid of all the segments. So hold on. So here you'll see a bunch of numbers that you can see on the screen that are basically the ID of the scans. So I'll explain later what the segments are comprised of. But these IDs that you see are aligned according to the distance it's from the laser base link. So if a segment is very near to the laser base link, it will be assigned 0, then 1, then 2. So it's like that. So this is what the one segment is made of. So if you see the image on the right, let's consider this 13th segment. So this 13 is the ID of the segment, and this blue line is the whole segment that you see, and it is comprised of a bunch of points that are clustered together. So if you see the message, the interface, you'll see it is comprised of an ID, the bunch of points, and then the centroid that I showed in the previous video, which is the cube. So this is how you will see it in the RViz as a visualization marker. Okay. So where am I? So now that the laser scans have been segmented into several segments, the task at hand is now to filter out those segments that do not match the property of a table leg. So now in this segment, if you look closely, only segment 7, 8, 14, and 5 is our original table that we need, and rest all is noise. We need to segregate all these points that are not table legs. So that is the real task at hand right now. So let me tell you what I did to solve this problem. So to filter out the excess segments, I have used, I've used various parameters to accept only those segments that resembles a table's leg scan. So these are the parameters that I have used to filter out the segments. The first one is the distance threshold, which I explained in the previous slides about the jump distance. And this is the primary filter of the segmentation. Now, all the other parameters are self-explanatory, but I will make use of the screenshots in the right to discuss these parameters. Firstly, minimum and maximum distance from sensor. So to give you an example, let me go back to the previous slide here. You can see some segments that are very close to the robot. So we don't need that. So to segregate these segments, you can simply use the this parameter of minimum average distance from sensor. So if you set it to something that is greater than the robot's radius, all of these segments will automatically get filtered out. Secondly, min and max point segment. So if you refer to the image at the bottom right, you can see the number of points in a particular segment, and that can be used to filter out the segments according to the need of the task. So for example, you can see that approximately it has 8 points in a segment, it has something like 10, it has something like say 15. So according to your needs, you can just set this parameter and you can filter it out whatever you need. So and the last parameter that I've used is the min and max segment width. So segment width is nothing but the distance between the first and the last point of the segment. So here, if the distance is 0.5, and if you have set the parameter which does not lie in the range of 0.5, then this segment will automatically get filtered out. So that's how I'm using filtering algorithms to filter out the noise that is there in the map. So here you will see the effect of tuning all these parameters. So earlier, this is what I had at the start. And after tuning some of the parameters that I have talked about, you can see all the segments that were there in the wall side has totally disappeared. But still, some tuning has to be done. So after tuning, you'll see this was my final result, which I could get to. I mean, I could have tried to tune more, but I didn't see the need here, because now you can see every segments that is present here resembles something that is like a table's leg or a chair's leg. So here every segments has a similar property of a table or a chair leg. So now I think the task at hand becomes very manageable, because just by looking at these images, this markers, you can clearly figure out which one is the pattern that we need. See, all of these are very random, and what we need is a table segments. So it gets very easy now. Now, if you refer to the image at the right, this is the algorithm I have used. It's basically, if all the points are randomly kept on the map, and you are given a problem to just find those points that create a square or a right angle triangle and segregate those points. So that's what I have done. Basically, you see all these centroids, which is just a point, and you have to segregate only those points that create either a square or a right angle triangle. If you do that, all you'll see is just the table segment. So I'll demonstrate that in the next video. So I'm starting the segmentation service here. So as you can see, only segments that are left are of the table legs and nothing else. I'll move the robot also here. You'll see that nothing else is getting detected as a required segment. Now you'll see this armchair is also somewhat like a table, but it has not detected it because of the distance separation between the legs that I have used to filter out those as well. And if you see those coffee tables and chairs, it did not detect them as our required segment. So I think it's working pretty fine. So with this, my LiDAR detection segmentation is complete. So now all it can see on Arvis is the table legs. So using this centroid, we can easily now approach the table and do all the tasks. So let me go to the next slide. So now that we have the table segments, the table legs, it gets pretty easy. Now, as I said before, the ID that is assigned to the segments is based on the distance from the laser link to the leg. So if this is the current situation that a robot is facing right to the table, you'll see that 0 and 1 are assigned to the front leg and 2 and 3 are assigned to the back leg. So all you have to do is search for the nearest leg, which is assigned with ID 0 and 1. So that's what I did. I use this 2 segment and I published a TF that is right in front of the table, and then the robot navigates to the TF in front of the table, and after that one more TF is created at the center of the legs of the table, and that's how it uses a P controller, and then robot goes underneath the table and picks it up. So it gets pretty basic right now. I mean, main algorithm that I wanted to show you was the LiDAR segmentation. So this is basically the flow of my code here. The basically 3 crucial packages that I've used is LiDAR segmentation, find table, and attach table. So I just explained what LiDAR segmentation do. It subscribes to the scan topic and publishes a list of segments, which consists of ID, points, and centroid. And we are basically we want the centroid of the segments as our to create the TF between the legs. So once the LiDAR segmentation publishes the segments, find table subscribes to it, attach table subscribes to it. And now let's see what find table does. It basically checks whether last 10 messages from the segmentation was received as true or not. I mean, it was received or not. So if you don't see any table in the map, it won't publish anything. So that's what it is checking. If it received any messages from LiDAR segmentation within in the history of last 10 messages. And the second thing it checks is whether the received message form a square or triangle or not. If it satisfies both these conditions, then it will publish true, and you'll see that table is found, and it will create a TF right in front of the table legs. So now that a TF is right in front of the table leg, we can use nav2 to navigate the robot to the front of the table. After that, attach table does something similar to it. It subscribes to the centroid of the front legs, and then it publishes a TF in the center of front 2 legs and follows the center using a P controller. So it's pretty basic now. Now I'll show you the demonstration of my services find table. So this is the condition. As soon as I called find table, you see here it created a TF right in front of the table. So here I'm doing it manually using Arvis, but in my code I've used simple commander API to like navigate it to the front of the table. And after it reaches the front of the table, I'll call the attach table service. You'll see here. So now it has created a TF right at the center of the legs. So once it reaches there, first it will orient itself to the orientation of the table, and then it will get inside it. So this was my project basically, but there were a lot of limitations, but I'll just explain a few of them. As you saw in my videos, you might have seen that the centroid marker arrays were not consistent. Like there were times where it flickers a lot. So I think possible reason for that could be the dynamic nature of laser scans, or maybe the code, the algorithm that I'm using to find the square or triangle in my map, that is of order O to the power n square. So I think maybe that could be a reason. So how did I handle it? So basically, I used a rolling window approach that looks for history of segments. So I looked for like last 50 messages, and according to that, I made my decisions to do whatever I need to do. So, but still, I think it's not consistent. It sometimes it gets very inaccurate. I think for the same reason that because of the dynamic nature of laser scans. So this is the limitation that I think still needs to be improved in my algorithm. So yeah, so where can we use this 2D LiDAR segmentation? So I think it's very interesting to not have any camera or any intensity LiDAR and still be able to detect objects. So I've I've mentioned some of the cases where we can use 2D LiDAR for object detection. So like in warehouse where there is very limited visibility, the lighting conditions are not good, and your camera cannot detect objects. So at these areas, I think 2D LiDAR segmentation would be really helpful. And for simple and consistent objects like in my case the table, you can easily write an algorithm to segregate them like I did just by looking for a square made in the map. So I think for any simple object shapes like the storage racks or boxes, you can easily use 2D LiDAR segmentation. And other than that, it can be used along with the depth camera to make your algorithm more robust. So for example, if there's a case where camera gives a false positive, so that can be verified with a 2D LiDAR segmentation if it actually is the object what it's looking for or not. So I think it could be really helpful to use 2D LiDAR just for object detection. And for future scope, and even in my project as well, I was thinking of using a machine learning model where I could use the data points, the segment centroids, and the segment shape to actually figure out what it is looking at right now. So I think this could be a really interesting idea that we could use in future. So that's it from my side. Now I'm sorry, you're not audible.
Yes.
Yeah, let's go for the demo.
Yeah. Oh, sorry. You'll have to wait for a bit.
What is that?
You'll have to wait for a bit. I got logged out because of inactivity.
Ah.
But we cannot see your screen. We only see your presentation.
Sorry?
Right now we can see your presentation still. We don't see.
Okay. Wait.
Yeah, there we
Can
are.
you see it?
Yes.
Okay.
Now yes.
So now what are we seeing here?
Yeah, Ricardo, could you wait for a bit? I think I have some problem with my network. I'll switch to my mobile data real quick.
Yes, of course. So yeah, because what we should have seen on the screen are the cameras of the lab that, in the same way that on the previous presentation, they were connected automatically to the project of Ritwik, and now he is switching to another Wi-Fi to see if he can get better connection for the cameras. We can see here, still connecting, and there I go. There are the cameras. We can see it really quick.
Okay.
Yeah, and then the table is not there. It's in another place.
Yeah, I asked Rodrigo to do that just to demonstrate.
Okay.
Yeah.
So the table cannot be seen on the image of the left camera. It can be seen on the image of the right. The other way around. Cannot be seen on the. No, yeah, no, I said it correctly. On the image of the left can be seen. It's the white one.
Yeah, 1 second. I'll explain that.
So now what are you launching there?
At first I launched nav2, my find table package, my attached table package, laser segmentation package, and right now I'm just launching my web app.
Okay. Are you going to control the whole system through the web application?
Yeah, I mean, it's just one button, pick table, so nothing fancy there. But yeah.
Okay, we can see now. You have reduced the screen somehow.
Yeah, I need to show you the status that it shows on the web app.
Okay.
Hold on.
So now we can see the two cameras, the RBIS, that still missing a localization, I suppose.
Yeah. It'll localize when I start the program. So I'm connecting to the web app now.
Okay. I don't know if you're doing something outside that screen. We cannot see it. Okay, just to let you know.
No, can't you see my web app?
No.
Oh.
Yeah, that's why I was describing what we were seeing, because I suppose that something was missing there. I don't know exactly.
I'm showing it to you, but
maybe you have selected just one.
Can you see it now?
Now we can see it. Yes.
Okay. So here you'll see all the status that is happening in the code. So I'll ask you to keep looking at it, but I'll also explain what's happening. So right now the table is at my home position. The robot is at my home position. So what it will do first is look in this area. At this area, if it finds a table, then fine. If it does not find it, then it will go back to this area. So I've kept up few points of interest to look for where the potential table might be. So I'll start the program now. I'm clicking pick table 1 here. So it's going to the potential region 1 right now, and then it'll look for a table, like the segments that I talked about in my slides. Yeah, so I have created 5 trials so that there's no false positives or false negatives. So that's why I'm checking it to just to be sure. So it will call find table service 5 times. So this is trial 4, trial 5. It could not find anything. So it will go back to potential region 2. Now you can see in the arrows that it has started detecting the table. Now it will create a TF between 0 and 1. It will orient itself to the orientation of the table, go in. I hope it does not hit anything. Uh, yeah.
So what is happening now?
So now that the task is complete, it's backed up. Now it will come back to its home position.
Okay. I just want to remind to the people, to the audience, that everything is being executed right now. It's in real time. It's being executed by Ritwik from his location, connected to the robots in Barcelona. So this is real stuff. So it's not video, it's not anything faked.
Yeah.
So what about the table status that you have in your web page?
I'm sorry?
In your web page, you have some area that says table status.
Yeah. That showed the messages what it was doing at the time of the task. So now, right now it has reached back to its initial stage. So there's nothing, it's just logging of what the robot is doing right now.
Okay.
Yeah.
Okay, great.
And the robot actions that you have on top?
I created this so that the robot could go to various waypoints, and you can, after that, you can just click find table. So if there's it's just for table detection, so that the robot goes to the position, and and when you press find table, if it's there, it'll show you the TF. If it's not, then nothing will happen. It'll show no table found.
Okay.
Can you go reach the table back?
No, I did not add that part, but I don't think that's tough task. I can do that, but I've not coded it to like go back to the back room and bring it back.
Okay, maybe you can send it by using navigation, RBS, and then press detect table.
Oh, right, sure. First, I think let me just localize it. It has like gotten very bad.
Well, that's an error regular. I think if you send it directly to the place, it's going to recover itself. For whatever the reason, I don't know why. So now you can press.
I think it has hit the leg. That's why it's not detecting. Wait, let me back it up a little bit.
You can use the joystick.
Yeah.
Of your web page.
Yeah.
The joystick of the web page.
Oh, that. Yeah, I'm sorry. I've not added the topics to that because there was a reason. Because I found the question that Rodrigo asked to Jēkabs, that when we use topics, CMD topics from web page, I think the robot reacts a little different. I don't know why. That's why I've removed that topic. I've not found the solution why it does that. So that joystick does not work badly.
We saw Rodrigo there.
Okay, yeah. Okay. So hold on. Yeah, so I think it's not showing on the table status, but when I click find table, you'll see no table found, table found. So that's why I've created 5 tries, because sometimes it cannot see. That's the limitation I was talking about. Sometimes it says no table found, but right now it's finding the table. No table found again, no table found, table found. So that's why I created 5 tries, because it's very inconsistent. Sometimes it goes, sometimes it comes back. But all in all, it's working. I mean, the table detection is working.
So when it doesn't find it, why it is? Because
I think because the segment messages that we are subscribing to, it's not consistent. Sometimes it just shows 0 0 and then it comes back. That was the limitation I was talking about. Like you see, it's fluctuating. It's going. It's very flickering right now. So I think that is the reason that sometimes it gives no messages at all. I think that could be that the reason could be my algorithm. Its time complexity is a little high. Maybe that could be the reason.
Okay, then thank you. Then anything else that you need to show us?
No, nothing else. I mean, you could
conclusions from your presentation
back.
or something?
No, nothing.
Okay. Okay, great. Then thank you, Ritwik. Thank you.
Thank you.
And now it's time for questions for Ritwik. Let's have a look at the questions that are on the chat.
Yeah, we have some of them. So, for instance, let's just start by this Rodrigo question. Mm-hmm. He says, how easily can your detection algorithm be changed to detect other types of objects?
Like, for example?
Oh, yeah. Can be changed very easily. Like, I'll show you the... Oh, wait. I stopped my screen share. Wait. Yeah. So if you see my laser segmentation code, there's a params file here. So all the parameters that I was talking about, it's right here. You can easily change your parameters from here according to your needs, whatever object you are trying to detect.
Okay, so I understand that then it can work for instance, other sizes of tables, but
no, not only tables. This has nothing to do with tables. It is just checking the points, the clustered points. That is the segment. So it has nothing to do with the table. Like suppose if I want to check a box, so it will create the laser scan will be a L-shaped line, right? So you can change this parameter according to whatever your needs are. So I think for that you have to change the maximum segment width. It could be more than 1, or you could change the maximum points that are there in your segments that you want. So that's how. I mean, it's not only just for table. Any object can be detected using this. other than this, you'll have to add some other algorithms like I did. Like I was looking for a square or a right angle triangle. But for basic filtering, you can simply use these parameters.
Okay. Yeah, makes sense.
So what are the effects that you can observe when on this flickering of the laser data? Is just an effect that doesn't detect the table or get wrong position of the table? What are the effects?
It's not wrong. I think there's a lag because let me show you my laser segmentation code. So yeah, here you'll see I'm trying to find a square shape out of all these points. So I've tried to make it of order n square, but I think at worst case it goes to order n4. So I think this could be the reason that there's a lag, like the robot still is like calculating the segments it is pushing to the lists. So I think this could be the reason that there's this fluctuating segments.
Okay, yeah, but I mean, what do you observe when those are fluctuating? It's just that doesn't detect the table. That's the effect.
Yeah, it does not detect the table, but for that I was talking about rolling window approach. Like I'm checking the past 50 messages. So if in past 50 messages you can see the table, that means you have that means the segments are there. So I'm using that to make my decisions to create the TFs.
Okay, and when you are doing that, the robot is stopped always.
Sorry?
When you are running the rolling window algorithm or option, then
the
robot is stopped.
Robot is stopped.
It's a stop. It's all under the same condition. Then all the detection.
Yeah, correct.
Yeah, could it be that you have false positives also?
I have never faced a false positive. That's why I demonstrated at the start that
that's right.
I brought it to potential stage 1, but it could not find it in 5 tries. So that means there's no table. In my experience, I've found that if the table is there, it will find it in less than 5 tries only.
Okay. Also wanted to ask you, because when we have run the demonstration on the first trial, when there was no table, right? On this area, there was no table, but on your map, on your global cost map, there are some obstacles that look like the table legs. So what are those? Why are they there in the cost map if the table is not there?
Because while I was creating the map, the table was actually there. So that is not a part of local cost map. It's part of global cost map. That's why you see those table legs there.
Okay. Does it affect your detection?
No, because I mean it would affect in path planning, but as the robot approaches near that area, the local planner adjusts itself to like go through it also.
Very good. Was just testing you.
Okay.
You can also remove them from the map manually, right? Just painting on top of it.
Oh, yes. Right. Yeah.
Yes. Yeah. And let me ask you another question. You check the so which type of footprint are you using when the robot is navigating?
The robot footprint, not the table one.
Does that apply when the robot is carrying the table also?
It does not, but honestly, I forgot adding footprints. I just remembered when you were asking Jēkabs about it. But I've never but yeah, I forgot adding it. It's there in my code. I wrote the function of footprint, but I have not added it in the main program. For some reason I forgot totally.
So it's kind of lucky then it didn't crash with the door then.
Yeah, that's true. No, but for that I have used my inflation layer a high inflation layer, so it plans the path from the middle of the door. So I've never faced a problem because of footprint publishing.
Okay.
Yeah, so let's go with some more questions here. Rodrigo is asking, so if I understood correctly, the robot goes to different areas to check for the table, right?
Yeah.
Then what if one of these goals, of these waypoints, is obstructed by an obstacle, let's say a person? What would happen in that case?
In that case, the square or the triangle that I was talking about, that won't be completed because it's obstructing the field. So the table will not be detected at that point. But if the person moves away, then it will find the robot table.
But it will, so the robot will keep trying to go to that waypoint, or for instance, after 10 seconds, because that waypoint is obstructed, it will give up and move on to the next waypoint, for instance.
No. That is also one of the reasons that I have added the retries. So each try takes about 5 seconds. So it will wait there for 20 seconds and look for table. Sorry. If it does not find a table in 20 seconds, then it fails. Yeah.
Okay, then another question is, why did you use a service instead of an action server? You use a ROS service in order to detect the table.
I did. I mean, I could have used action. I don't have any answer for that, but I don't know. I mean, it works pretty well with service.
To table, right?
Yeah, to attach and to find. Yeah. I mean, it works pretty well with service, so I didn't find the need to like add actions, but yeah, I could have done that also. Does not make any difference to the performance of the robot.
Yeah, well, the important point here, for example, for detection, it's a service. It's a service because you just launch it and wait for the answer. Then for attaching to the table, the robot has to perform some movements, and those movements can fail for whatever the reason. And for that reason, it is more convenient to use an action server for the attach, because you can be providing feedback about what is happening in the process of attaching. Like, for example, so I'm approaching the table. Now I'm starting to get underneath. Then I have lost the frame, whatever, in case that there is an error. So I'm stopping and going back in case that you implement some recovery behaviors for that. And also it's interesting because it can be aborted. So you can stop it and say, hey, wait, stop. Because you're going to crash or something. That's why it's more convenient to use action servers. It's very fine detail, but it's interesting to understand that difference.
I have one more question. So I can see there from your global cost map in RVs that you are also using keep-out masks.
Yeah.
So in your case, for what you are using those?
I used it just because, like you see here, the coffee table area, the scans were not accurate enough. Like, it's just showing one line, 2 dots, but in reality, there's a lot of table legs and chair legs. So I don't know why it was not captured while I created the map, but just to compensate that, I have added the mask here.
Okay, so just to make sure that the robot doesn't go there.
Doesn't go there, yeah.
Okay.
What about this question?
We have a question here from the last one from Girish. He says, if the pattern detection algorithm can find square and right triangle, can you just use the triangle to continue with table detection?
No, I've written the code such that it searches for square first, and if it does not find a square, then only it goes for triangle. because there could be many reasons that if I navigate it to the coffee table right now, there are chances that it might see some triangles there, and it will detect that as a table if I do that. So that's why my first priority is to check the square. If worst case it does not find a square, then it checks for the triangles.
Okay, understand. Okay, so I think we could leave it here already. So yeah, thanks again for the presentation, Ritwik.
Congratulations for your
Thank you.
Masterclass title.
Yeah, thanks a lot. So yeah, then we are going to move to the last presentation. Bye bye, Ritwik. We are going to move to the last presentation, which is going to be performed by Peera Tienthong, and he's going to introduce also a new robot to us, which is the RB1. It's based in our warehouse lab. So meanwhile, Peera joins us here. So his project is based on a warehouse environment, and he's going to be using a navigation tool also, combined with behavior trees, in order to automatically detect a shelf in the warehouse, no matter where it is in the warehouse, and then it can pick this shelf and place it wherever he wants back. So
yeah, his project is very interesting because so we have this warehouse where the students are practicing remotely, and then what happens is that they are taking the shelf of the warehouse and then leaving there somewhere else, and then next student has to grab it remotely, control the robot, get underneath the shelf, put it back, and so on. So every student can use it. But we thought, oh, that could be a very interesting project. So if there is a robot that when one student finishes the class, then it can be so, oh, here is Peera, so maybe he can explain better the project. Hello, Peera, how are you doing?
hello.
Hello, can you hear me?
Yes, we can hear you clear and
Hi. Thank
loud.
you for having me here.
So all yours.
Pleasure.
All yours, Peera. Explain your project.
Okay, I will share my screen first.
Yes, please.
Can you see my screen?
Yes, there we go. Yeah, we can see it.
Okay, all right. The goal of my project is to develop the new behavior for the RB1 mobile robot. So this behavior is constructed by like a small behavior. It's like you are building a Lego model. So you need first to have the small piece of the Lego and like stack them together to create the complex shapes. So this one applies to this project. So okay, I will go over each topic. First, I will start with the system description. So the requirement of this project is I have the mobile robot in both the simulated and the real world environment. Also, so the robot has to detect the shelf in the warehouse. So it doesn't know where the shelf is, and it doesn't matter where it is. It needs to find its way using the navigation stack and move to the front shelf, orient it, align it to the shelf, go underneath it, lift it, and place it in the desired location based on the user. So I have to explain about the concept of behavior tree because there's some terminologies involved later. So the behavior tree is like is a tree structure. that combine the small elements to make the complex structure of the behavior. So is the concept that come later from the finite state machine. And the advantages of the behavior tree is to create the modular design. I mean, if you're familiar with the finite state machine, so you might know that to connect state from state, you need to like have the condition, and the condition is like when you're building you need to connect like wiring. If you imagine like electrical system, you need to do a lot of wirings. But the behavior tree, you won't do that. You first create the independent structure, independent nodes. You can see from this picture that this one is the simple behavior, like the robot find the ball, pick the ball, and place the ball in a place. So it's construct from find the ball. And this one doesn't care the condition where how to pick the ball. Just search for the ball, and then do the pick ball, and finally place the ball. So the modular design means you construct things. For example, for the pick ball, this may be composed of like smaller, like the leaf node or smaller element, like they take the ball and approach the ball and grabs it. So this kind of the modular design, and also the behavior trees promote the reactivity. That means you don't have to do a lot of wirings. If you need to update the system, you just worry about the independent action or node. You don't have to worry about the entire system or do the rewiring again. So that's cool stuff, and it's kind of convenient. And here's my my project, my software architecture. So I have the high-level behavior tree. I will show you later how it looks like. And the smaller element, I connect together the navigation system, the shelf detection module, shelf attachment, and shelf detach module together. All of this is done based on ROS action and ROS service. Also, it's kind of convenient to visualize the high-level behavior based on the group visualization. This is the software that visualize and also edit the behavior tree in real time. Also, I have the highest level for the end users to control the entire system by using the web application. So this is how I set up the navigation system. I use the SLAM toolbox library. This is kind of cool if you familiar with it. It can create the map in real time and also save it for later use. So I built the map by SLAM toolbox, and then save the map and use the Monte Carlo Monte Carlo server, like as usual as we familiar with. So the step is to create the map by SLAM toolbox and config in the AMCL YAML file, and set the global localization, and also launch it for navigation system. So okay, and there might be the following challenges based on this, which is I separate the simulation and the real robot. So it's different. For example, the frame ID is different. The frame name is different. The size of the robot different. The inflation radius or any other parameters is different between the two environments. So I separate the two sets of configuration files, one for real robot and another is for simulation robot. So, okay, I will then launch the simulation. So for you to visualize, give me 1 minute. Okay. You see the screen, right?
Yes, we can see it, Peera. So you want to test now with the simulation environment?
Yes.
Okay.
Yeah, here's the simulation. So this is to show the concept of SLAM toolbox, but we can skip for now if you want. Yeah, I will explain more interesting topic. Okay, so yeah, I to design the system, I need to keep in mind the difference between the real robot and simulation robot. So for example, in the real robot, the laser scanners like fluctuate all the time. So it's kind of noisy. So, but in the simulation is like stable all the time. And also for the real robot, the elevator to lift the shelf like takes some time for the delay like to reach the maximum height. So I need to put more delay on the real robot, but in simulation is not necessary. And also the controller is also different. I noticed that for the real robot, the controller is more reactive than the simulation. I think this is because the controller that applies to the gazebo simulation is like kind of like slow. Yeah, and also any other aspects is different. So okay, the next topic is to explain, like as I explained earlier, the behavior tree depends on the smaller elements. So I will start with the navigation. So this is how the behavior tree connect to the navigation stack. So by using the action, the action node. So at first I have challenges. I got stuck to create the asynchronous communication between the navigation stack and the high level tree. So I solve the solution by using the behavior tree library. So this library is create the wrapper for the behavior node to connect with the navigation stack. So for example, this wrapper includes the action client, the service client, and the topics and subscriber. So it's kind of like a fast implementation if I use this library. So yeah, the library is created by the behavior tree developer. Here, this is integration with ROS2, and I use this public library here. Okay. So, okay, there might be some variations in navigation node. This includes the navigation to the predefined location, navigation to the detect shelf location, and lastly, navigate to the desired goal. So to navigate to the predefined location, the robot, I have the location saved in the YAML file like this. And yeah, I will, yeah, this is how the behavior node look like. And the second one is to navigate to the shelf location. This shelf location is detected in real time. So I put it as the variable in the behavior node here like this. And lastly, navigate to the desired goal. This goal is specified by the user, but the only thing that user need to modify is the goal orientation. Right? For example, 45 degree here. So, okay, to achieve this desired goal location, I use the publish point available in the, yeah, I will show you later, available in the Iris interface. The second thing is the shelf detection node. This one I separate into simulate robot and real robot. For the simulate robot, yeah, I face several challenges. The first one is in simulation, there is no robot card frame published. So I need to create the front shelf as you see in the picture here. The robot need to move to the shelf frame here, but it cannot move to the, it doesn't know where it is. So it need to rotate itself and move to the front shelf. This is the front shelf frame I point here. The second problem is robot cannot move to right away to the card frame. It needs to move to the front shelf by using the navigation. Here's the front shelf as my mouse pointing here. But this problem is not exist in the real robot because this frame is called robot card laser frame is published and in real time. Yeah, so I just create the front shelf frame here and robot move to that point. And also the difference between the simulation is the laser intensity is noisy. So I need to create the threshold to make and adjust it by trial and error until it's robust enough so that the robot can detect where the shelf is. So the third node is the shelf attached node. So this node, the robot needs to move underneath the shelf, lift the shelf, set some navigation parameters. So yeah, the first problem I face is that the robot cannot move to the front shelf precise. I mean, falling from the detection, right? There might be some error from the navigation between the front shelf frame and the robot frame. So I need to create another frame. Yeah, I need to create the card frame, and so that the robot can move from its current location to the card frame by using the control loop. So in simulation, the robot just oriented to the card frame here. Is moving to the card here, but it cannot align because there is no reference frame for the shelf. So I use the the detection server. I will show you how, but the robot will rotate from its current location. It will rotate to the front shelf so that it can move forward. And for the real robot, the problem I face is the robot cannot get close to the robot card frame because this dynamic frame and will disappear when the robot get close to it. So I create another helper frame. It's called the temporary card. So this one is in front of the card laser frame. It's like offset in the front, and the robot can do the orientation and alignment to the temporary frame before moving forward to that. So, but at first I create this frame as the static frame without realizing the noisy signal. But later I found that the robot cannot move underneath like precisely. It may crash a little bit. So I do it by using the dynamic frame. This one is reference to the robot card laser, and so robot by using the control loop, it can move, it can orient to the temporary frame and align it to this frame precisely and before moving to the underneath the shelf. And the next one is detached node. So this one is quite simple. The robot, when it's reached the final location, the robot the behavior tree activate this node, and this one is to lower the elevator and move back, and also set the footprint back to the circular radius footprint. The next one is the backup node. This is for the safety purpose. So when here you can see from the picture, the robot already has the shelf and is in the gray area, so it cannot navigate to the goal. So that's why, to avoid that problem, I create a backup node to back up for a specified user-specified distance, like for example, 60 millimeter here. So the robot can do the back up to the free space before navigating to the goal. So after developing the algorithm, I do the testing here in the simulation by place the shelf at the different locations, so to make sure that the robot can find it. So I can show you first in the simulation and later in the navigation. Oh, sorry, in the real robot.
Robert, sorry, Peera.
Yeah.
So for the demo, I think I would go directly with the real robot
one
later. So you can skip this one, the simulation.
Okay, sure. Yeah, I can show you in the demo right away. I think is. Let me open. Here is the real robot connection, and I'm gonna launch the navigation nodes. So is launching the navigation, and I'm gonna launch the Always launch. Okay. Okay. Then I'm gonna launch the shelf servers. This combine everything about the shelf. So you can see the suffix real here. So as I said, I separate between the simulation and the real environment. This is the real environment. So the next one, I'm gonna launch the behavior tree server. And also I'm gonna launch the web application. So and second, I'm gonna launch a Raj bridge. Server. Okay. And gonna get the web address, web page, and also Raj bridge. So okay. Here's my web page. Okay. I'm gonna connect to the application. You see my application, right?
Yes, Peera, we can see it.
Okay. I connect it and I choose the environment. It's a real robot environment. So the first thing I should do is to check the status of this topic and service, whether it's available or not. So if it's available, it's gonna turn green here and the service and all available. So I'm gonna check first the elevator. Is it activated? I put it on here. So I don't know why it's not activated. Okay, first I gonna do the global. This is I gonna do. You can see that the sensor and the map is not aligned. So I'm gonna do the localization by pushing this button. So here you can see the robot should move to the home position, but it takes a bit. So here it's gonna navigate to the home. So when it's finished, you can see the alignment between the the laser and the map. So it's finished. So we can click the button, just signal how it's finished. I can switch between them. If I can you see the screen, right?
Yes, we see both.
Okay, sure. Okay.
But now the cameras are gone, yes, but it's okay. It's okay. We can see on the Orbis also.
Yeah, you can open the cameras there. No, it's another. Okay.
Okay, here the robot is at the home position. So I can manually go over each action here. If I click the detect card, if I click the detect card, so it's fail. The behavior tree says fail because there's no card there. The next one, if go to card. So this one is the service that if the card is found, is removed to the front. But we expect that it should fail because there is no card. And the attach is to move underneath. So this one is the I see the robot move, but just stop it. I think it should not. Yeah. Anyway, okay, I see is
that a service or an action server?
That's the service. That's a service. Okay, I will move it back to the. Okay, I disconnect again and I will move it to home again. I put it off.
Now the elevator is on. Huh? I can see.
Yeah, now it's on. You should off. Interesting. It's not off. Oh, it's off. Okay,
it's getting off. Yeah, because you take some time.
A little bit.
There's a little delay. Yeah.
No, but it's going up and going down. It takes time for the motors to push the robot up and so on. So if you press many times, then maybe it will go crazy.
Yeah. So okay, it's at home already. So the behavior tree say it's done. The tests all done. So I gonna trace the full behavior. So this one is gonna do like combine all things together and like go to each other. So now the robot will move to the first detection location. If it cannot find the shelf, it's gonna move to the next detection location. So I place a lot of detection locations here. So here is the second location, if you see. You can see from the server that the behavior is running. And the shelf file is no, because there's no shelf there. So again, the user can also set the goal location by using the publish point, this point here in the Alvis. So if I set this point here, I place the shelf here. Okay, so go back to the camera. So now it's found the shelf. So it's gonna orient to the shelf. To the temporary frame that I said earlier. And now do the alignment to the front. I said it's for slow speed in order to like for the safety purpose. So it is now it's lifting the shelf here, and it's gonna do the backup. If you see from the this here, it's gonna move to the free space. Remember, I press the goal location here so that the robot will, it will create the goal frame. Sorry. Okay, it's gonna do the attach shelf this, and then move to the, like, repeat the process. Yeah, move to the first location and wait for a signal from the end user. Okay, that's all. Here the behavior is done. So, and the footprint is set back to the radius. And we can also repeat the process again by pressing this button. The robot will move again.
And can we, Peera, see live what is going on in the behavior tree?
Sure. I will show you in the visualizations. So in the GROOT is the software. So open it. Here's the GROOT. First, I will check first is the license. So now I already, in order to visualize like more than 20 nodes, I need to have the license. So I request for the license from the developer and activate here. So I will open my project. So, okay, this kind of cool application because you can edit the behavior tree here without like doing manually in the XML file. or you can monitor it in real time. So I set the port to 1667. Here, I connected to the port so you can see in real time what robot is doing. So the red color mean that the task is failed. So if the task is failed, if move to the next task, which now is currently doing the, you see the yellow color here. So it's currently doing the shelf detection here. I can explain what was the meaning of each one, but it takes some time and
yeah, no need. Then what is happening with the robot? Is it still moving between locations to look for the shelf, right?
It's still looking for the shelf, and yeah, it's found the shelf here. You can see from now is here.
It turned green, one of the behaviors, right?
Yeah. Remember, I set the goal location here, so it's overlap, right? So I would play this another. I will play this here. Yeah. So now it's moving on the shelf. If you see from root, yeah, you see the green color. That means the task is finished. And now it's doing the shelf approach. Shelf approach. So like this. Gonna back up. And remove here.
Hostia, una cámara se ha quedado friseada ahí.
Oh.
Ah, porque la ha parado.
I think the robot crashed the shelf a little bit. You can see is here. It's like the shelf here, the card here is like collide with this one. I set the goal too close. It's not there for more space. So that's why it's yeah. Okay, all right. There is a situation where here, for example, the shelf is like overlap the detection location. So if this the case, the robot will skip that location and move to the other one. So it's not collide with the shelf. So apply timeout, gonna connect. Okay, let's go back. Here is gonna move to the detect location. Oh, what happened? I think
So what happened there? Why did it collide?
I think the cost map is too close to the footprint. Yeah, so that's why it's collides. So the robot see, the back leg of the shelf, and that the back leg is not detected as the obstacle, only the front. So that's why when it's moved, is blind to the back shelf.
But why is not? It should be detected because there is an object and then the lidar should detect. No?
There in NRVs at least it appears.
Yeah. Okay. So okay, I will start again. I set the new goal. the robot moved to the next detection location. So because the server is still running while the client is off, this it's gonna move back again. Don't worry.
So do you have a way of interrupting, aborting the
Yeah, I have.
behavior?
I can shut down the server, but I did not do that. I can shut down the server. Yeah, it's moving back. And repeat the process. Okay. Now it's found the shelf right at the start, so it's moved right away into the shelf.
So your algorithm can find the shelf since which distance?
So it doesn't matter where the robot is. So if it can detect the shelf, it will move right away to the front shelf.
Okay.
Yeah. So right now it's keep all the other detection location, and from the first location it's moved here to the front shelf. He's doing backup. Is for safety reason. And there is I found a problem, which is the robot moved to the front shelf, and when it's moved back, it doesn't know the distance for the backup because I use the speed control. But right now I use the the proportional control loop, so it's know the distance between the distance for how long it's gonna do the backup. And I ensure that when the robot found the shelf, the distance from the front shelf to the shelf is longer than the backup distance. So when the robot do the backups, it's safe and won't crash anything. So right now it's trying to move to the goal location, but I think it's got stuck in there. It's got stuck. So yeah, all we need to do is to wait for the behavior to fail and set the new goal so the robot can move there. Yeah. Just need to wait for the timeout.
What it's doing now?
So it's, I don't know why it's moving to the goal, but this is the navigation issue. Here in the group, so you see it's doing the it's moving to the destination by the navigation stack, but it's failed.
Now it went.
It's failed, so that's I just set the new goal location here, so that's why I changed from the middle location to the here, and it's complete. Okay. So right now is finished the detached shelf, and we move to the first location, but I think it's too close to the shelf. I solved this problem by adjust the parameter, like how long it's gonna do the backup. Here I do the I set the behavior, no, the parameter for the detach. So we can set, so right now is like 0.8 meters. I can set it more to 0.9. Yeah. I will bypass the robot. Okay. So now yeah, here I set the in the detach server, I set the backup distance to 0.9 meters. So just longer than last time. So it can navigate to the avoid it safely.
¿Cómo?
Okay, I think that's all for my presentation.
All right, Peera, can I ask you to run it one more time meanwhile we talk, so that you leave it where it should be for the next students that are coming later? Okay. Yeah, so you just need to run the behavior tree again, right? And then select the end position.
Yeah.
Okay, then thanks, Peera. Let me give you some. Okay.
Okay. I keep it running. That's okay.
Yeah, leave it running. Leave it running, and then at the end you just select the and then meanwhile we are doing the Q&A, we keep testing a little bit more the program.
Yeah.
Okay, so let's go with some questions.
Sure.
Then. So okay, yeah. So how much more complex is to build all this with behavior trees compared with a regular approach without including behavior trees? First question.
Yeah, like for example, just going with if-else sequences.
So the structure, as I said earlier, is modular. You don't have to worry about the condition. The condition is defined in the behavior tree, and also the end user, if they, for example, they can create the behavior tree based on the XML format like this by themselves, or they can do it in the group. They can if they have the small element, for example, the take node, the attach node available, they can like drag and drop, like building the Lego here. So the condition, as I mentioned, is not like if else, like text programming, but here is like the sequence, the fallback. So it's kind of different way to take the tree. So all you have to worry about is to create the small element, small node.
So you create these boxes, right? You program these boxes, and then once you have them, you just put them as you want in the.
Let me show you here. Here am I in the editing mode, right? So here my main tree is here. It's like this. So the available node is here. You see the custom node is highlighted in the blue. This is the node that I created. Yeah, but anyway, there is provided nodes here. You see in the black provided node. Or you can use if else, you can do anything from here. You can do the pick and place like this and connect them together. This is much more convenient than doing from like the regular method, I think.
Yeah, also I would like to support your decision of using behavior trees, because I think that the question of the person on the chat that is asking this question is because it looks to him probably like a lot more complex to do all those things rather than just go to the code and then put the conditions with if else and then jump here or jump there based on the if else conditions. But the problem is that this only works when there are 2 or 3 options possible. So if this, else this, then it does work. But for a complex behavior like the one that you have there with many possible options, then it starts to escalate into a lot of special cases. So you, with the behavior trees, you can manage all those things in a better way, in a more encapsulated way, in a more compressed way, I would say.
Right. So I would say that if you are 100% sure that your small element, for example here, the attached shelf element, is working well.
Exactly.
But the behavior is not what you expected.
Yes.
Maybe because that maybe because you need to rewrite the behavior. If you cut this one here, for example, and do the rewrite to the the next thing here is quite easy, as I say. But for simple system, it's not necessary. But for more complex system like this,
yes.
for example. Yeah,
Okay. And can you show one of these behaviors, the code, very quickly, so that we can have a look at how it looks
Sure.
like?
Sure. Okay. So the code. Okay. First,
So
I create the node, like the ROS node as usual. Here, for example, the shelf attached node is the service node. Like usual, the structure is like we have service callback and that's our algorithm about the the frame transformation, anything here. Keep in mind that this is the server side. The ROS service is on the server, but in the behavior tree is the client side. Here is, for example, shelf attached behavior like this is on the client. Like you set the request to the server and it's gonna get the response from server like this. Thankfully, from the library that I mentioned earlier, it has the wrapper for the raw service. Here you can see the on response receive or set request. They're from the web wrapper itself. The library is so convenient. And yeah, this is the client side. Also, if I complete constructing the client here, I need to register to the main tree because that is the small element. It's just a one here. It's just the blue, the highlight blue here, the node. All I explain is just here. So I need to register. The register node will look like here. Will be in the XML file like this. For example, the
yeah, so basically this defines how the different behaviors are connected between them, right?
Right. For example, the attached shelf. This is the register node. This is the attached client. This one is similar. No, I mean is exactly the same as this one. Here, the attached.
And if you do a modification here in the graphical interface, that is applied to the XML?
Right. So if I modified it and save this thing, it's gonna create the XML for me. Yeah, you don't have to worry to write XML yourself. You just edit here and set some parameters here. That's all. And this parameter is the request from the client to the server, and server receives this data and do the calculation itself.
Okay. I have another question related to your localization system. When the robot is initialized, everything in your behavior tree, I think it's at the beginning, is you start with the localization, right?
Right.
And then So can you explain us how does it work, the initial localization? What do you do in the initial localization? Because there are one question there, another one from me. So if you can clarify.
So here, here in the first of all, I create the map. The map that I created is,
Yes, on the higher level. Explain us
yeah,
the steps.
Yeah, the map is created by Slam Toolbox.
Mm-hmm.
And it's in the map server here.
Yeah,
the file, the YAML file and the PGM file. So I use the AMCL node.
Yes.
Because at first I try to avoid this one, but I just using the Slam toolbox to do everything. But for the real robot, I cannot do that because every time I start the navigation, the map frame, which is the most important, is like this place. So so that's why I need this AMCL to make the map frame static at one position forever. So and also I set this parameter, set initial pose to true. Sorry.
Okay, but you were doing something like moving the robot around, and also you cannot know that the robot is going to start at that position.
Right. First, I set this to true, so that is like predefine the location first to avoid the gray area. Because at first the map and the laser scanner is not overlap. It should overlap, right? So once I click the home button, it's gonna move. And when it's moving, the laser scan is like converging to the current location. This is enabled through the global localization when I set to the robot.
But are you doing global localization or are you doing initial position localization?
I do the global.
How?
I first enable the global, but I found out that sometimes the robot position and the map is random. It's like the robot overlap to the gray area and it cannot move out itself because it's got stuck there. So that's why I need to set the initial position, like to at some point make it on the free space, the white area. So then it can navigate and the global localization do the things.
Okay, so if you are doing initial localization, there is no global localization. Global is when you spread the particles over the whole area. And initial localization, you are putting the particles at one specific area, one specific space. I mean point, sorry. Point.
Okay.
Okay. Then
Then
you start moving the robot, right? Because
right.
in order to make the localization algorithm correct the error.
Yeah, right.
And that movement, does it take into account obstacles?
Yes.
How?
So the global localization will converge itself, and I can show you again now. I will show you again. I will restart the navigation server.
Okay.
Let's see.
Yes. Yeah, so many tabs.
Here is start the global localization, and you're right. So right now, the robot see the obstacle. and it's on the border of obstacle.
Yes.
Because of the laser and the map is not overlapped. Right? And this point is created using the initial pose.
Okay.
But yeah, I can move it to the home position if I click this. Oh, I need to, sorry, again, launch the server.
Yeah, to receive your command. Yeah.
Okay, sorry. All right, that's all. Okay, and go home. Here is start moving. It's converging.
Mm-hmm. So it's using path planning to move?
Right.
How I should. Okay. I see.
So
you're not printing the path. You are not printing the path, but it's using navigation. Okay, I can see. It's because I couldn't see the path before, and then I thought that maybe you were just moving yourself randomly, but no, it's following a path, right?
Right.
Okay, understood. Okay, do we have more questions?
We have one from Girish here. Let's see. So Girish is asking, why do you require a maximum of 40,000 particles and a minimum of 1,000 particles for AMCL? Is that something?
Which can you point out what?
It's the well here actually it's another values. Yeah.
Here, right?
Yeah. So did you have to tune these for something or?
I think it's the default value. I think I did not tune this thing.
So we don't know from where
it
took those values?
Probably from another file.
So I think is the value is like on the rate particle here. I think is to accelerate the process. I think if it's too high, it's gonna take some more time.
Yeah, exactly. Yeah, that's the number of particles. But I guess that Girish was wondering that maybe you have specifically set these values for some reason to that. But I think you are using just the default ones, right?
Yeah,
for that space is good enough. Those values that you have there are good enough. Okay, so more questions?
No, I think we can already leave it here. So, thanks a lot, Peera, for the presentation.
Thank you so much.
Congratulations for your title.
Congratulations. So, congratulations for your title for the masterclass. And so we have finished it with all the presentations already. So, I think it has been a very interesting day. We've had many very cool presentations. We have seen all the demos with the real robots, even one with his own personal robot. And we have been around many of the robots that we have here in our office. So, I hope that the audience has enjoyed all these presentations, that you have learned some more. And if you want to be doing your own presentations here in the future, check out our Robotics Developer Masterclass. Yeah? So you are going to find the links in the description and so on. So, then I think we can already leave it here.
And congratulations to all the students, because you got your master class degree. So that's for sure. And then we'll contact you for the next step, which is
internships.
The internships.
Mm-hmm.
Excellent.
So stay tuned, because we are going to be in touch in the following days.
Thank you very much, everyone.
All right. Bye-bye.
Bye.